don't think anyone watches it. I really don't. Some people do. Some people do. I'll admit there's probably like 3 people, and everyone else is like, bro, I got like dinner tonight. I'm gonna go like hang out with my family. I'm gonna go
So
hang out.
I shouldn't say this in recording. I
Yeah.
won't say it. I'll be back.
Why not? It's okay. I don't judge.
I just need to pee.
Man, I wish I had a boyfriend to go hang out with.
She's like, I just need to pee, so don't record it.
All right. So, they both left. Okay.
Yeah.
I'll pause it. Yeah. Should I probably go over that again? Okay. So, not type 1.
Yeah.
What? What's up?
Nothing.
Nothing.
I think my computer's lagging. Sorry. Go ahead.
Okay. All right. So, type 1 alveolar cells they're 95 to 97% of all the alveolar cells, and have gas exchange within them, and the walls of them are very thin, which makes sense because to allow for diffusion. Now, type 2 alveolar cells, they secrete surfactant, and surfactant basically stops the water which is in the alveoli from forming these bonds called hydrogen bonds, so that they don't collapse when you exhale. And if, let's just say, you didn't have surfactant, that whenever every time you exhaled, your alveoli would collapse, and that's really bad. We don't like that. But surfactant basically stops the water from hydrogen bonding and stops the surface tension so that it can, open, or like basically get smaller and bigger without having to collapse, without collapsing. All right, so this is just showing you like what it looks like and how the capillaries exchange between, you see how this wall is really thin, and that's how it diffuses across and all that stuff. And these words I'm never going to talk about again. I mean, she said they're made of simple squamous epithelium, which makes sense because that's like one of, if you ever went to anatomy class with the the microscope, and you look in the microscope. I mean, I know Morgan did because we went to the same school, it's not the same teacher, but he made us look at the slides with different, basically like tissues, tissues. I don't know. And then you look, and some of them were like box shaped, and and some were like, I don't know. There were different types, and this is one that's very thin and very simple squamous epithelium. And there's pseudostratified columnar. There's a whole bunch of them. Not like I ever will remember any of that, but it helps. Okay, so the alveolar cluster and alveolar sacs, and their ends of the respiratory bronchioles. There's very thin air tubules, and they end in alveolar sacs. And yeah, it's pretty simple. That's just showing you a picture. And the respiratory zone is where the gas exchange happens, and the conducting zone is where the basically like when the air gets humidified, heated up, it gets cold. Hi, Nelly. Hi.
Hey.
How you doing?
I'm alive.
Well, that's good. We like alive. I mean, it's better than dead. I mean, I'm
alive, but I'm dead.
Me too. We're together. Okay. All right. I was talking about the conducting zone and the respiratory zone. And the conducting zone is basically when, like, every other part than where gas exchange occurs, and the gas exchange occurs in the alveoli. All right, so this is just showing you. Wow, she has an active speaker note video apparently. What? I don't even know why that's popping up there. Maybe I should go to slideshow. Maybe that would be better. Okay, well, it didn't go away, but okay. All right, so like I said before, the respiratory zone is where gas exchange occurs, and the respiratory bronchioles and the alveolar sacs and the alveoli. I doubt, she said that she's not going to ask you that, but if ever in our careers does this come up, then better to know than not. Conducting zone, basically structures that carry air to the respiratory zone, warming of the air, humidifies the air, and filters particles. There's this thing called the mucociliary escalator. And this is basically how they get particles that are higher than 6 microns out of the respiratory zone, and allows them to, be filtered out. And so that you go, I don't know, I can't really like that, it gets it out so that you either swallow it or you cough it out or you spit it out, whatever you want to do.
Did she mention that name, the mucus?
Yeah.
She did?
Mm-hmm. But she did. I just feel like it's going to be relevant in our careers. So that's why I talked about it. But doesn't mean you need to like stress over it. But if you ever hear it again, that's what it is. That's what gets the stuff that's not good out of your lungs.
But that's good. That's like the cilia, like all the respiratory tract. It's all the lining. It has the cilia, and the cilia has like a mucus I don't know how to say that, mucus. And then every particle that exceeds that amount, it's trapped there, and then the cilia just spits it up and you cough. So that's just always going to be in the lining of the respiratory tract.
Yeah, and there's so this is what I asked the teacher was, what about cystic fibrosis? How is that relevant? And there's well, she said it so beautifully, but there's a chloride channel something that basically is not working because the DNA is not good. It's a problem with DNA. And basically then that mucosal layer, one, it's thicker, and this doesn't work. So things get trapped in there. So, Hi, Jackson.
Hello. Oh, I thought I made the video. How you doing?
Excuse me. Were you okay? We were waiting for you.
I'm sorry. I just got home.
Sorry, nothing.
Jocelyn, I just got home. Okay, how y'all doing?
That's what happens for being like the only man in the group.
I know. Well, where is James? He's not here tonight?
He's not here tonight. He works. Yeah.
I'm paying attention. Okay, let me let you do your thing.
All right, so the resident alveolar macrophages will cleanse alveoli. Macrophages means eat, which makes sense. So it eats stuff, and I don't know. Apparently they cleanse them. Okay, whatever. I don't know. She didn't talk about it, so I don't talk about it. This is what I was talking about, the mucociliary escalator right here. It traps it and then moves it up so you can cough it out. Isn't that a pretty picture? Does everyone see that? Isn't that so pretty? I thought it was so pretty. Okay. Anyways.
There is definitely tree.
It's so pretty. Anyways. Okay, so what does the diaphragm look at rest like?
Like the dome shape.
The dome shape. And when you breathe in, then it expands downward and bigger. So how I got through my HESI exam was they asked a lot of stuff on respiratory. I knew nothing because I spent all my time on other things like just endocrine. Okay, just that. Not just that, but other things. So literally you just saw me in the in the room just going like this. I don't know what it's I'm just trying to make it so that I did pretty well, so maybe that's what, I don't know. Anyway, so like if you're ever sitting during the test and you're like confused about the diaphragm, you can imagine that it's a muscle. So when it's relaxed, it's like upwards, and then it comes down to expand because your lungs are expanding and getting bigger. All right, so the parietal pleura, that lines the cavity, right? And the visceral pleura is what covers the lungs. Now, in between that, it's the pleural cavity. And before we talk about it later, the pleural cavity is referred to as the intrapleural, oh my word. Space. Pressure, but we're talking about more about pressure later on. So it's the interpleural space or the interpleural pressure is what we talk about later on. And this is basically, it should always be, the pressure in that should always be less than the pressure in the lungs. Because if you can imagine, if you have a higher pressure on the cavity in which the lungs are in, then this would put pressure exceedingly on the lungs and cause them to collapse. So that's what she was probably talking about earlier today, because I mean, I don't know, but from what you, like the little you explained, that was something that is relevant. And so whenever there's blood or air that gets in that intrapleural cavity, it causes more pressure and causes lungs to collapse. And then they have to put the chest tube in, and there's a specific word to it, but it's basically a pneumothorax or something of the sort. So
what do you say about the interpleural pressure? Does it have to be higher than the lungs, you said?
lower.
Okay.
Always lower. So when we're talking about the interpleural pressure, if it's above, then that's really bad. We don't like that. We're dying. Your lung is collapsed. So we never want it above the lung. Okay. So, and there's and what causes this pressure is the thin layer of fluid in the interpleural cavity. That's what the pressure is from. But it's not much. It's not much. It's just a little bit below the lungs. This is showing you the most beautiful diagram of the diaphragm. Oh, wasn't that fun? No one thought it was funny. Okay, well.
I got it.
Your reaction is funnier.
Anyways, so this, it's pretty, that's, yeah. Okay, so this is what I was talking about, the interpleural space. There's a thin fluid layer, and you don't need to know everything, but it's secreted by the parietal pleura, which, doesn't really mean anything for me. And the function is to lubricate and allows the lungs to move without friction, which makes sense. Okay.
You were saying that thin fluid layer is what gives that like small amount of pressure?
Yes.
Okay.
That's what she said.
Yeah, that makes sense. Yeah. Thank you.
Okay, guys. Well, we're not going to look at this slide while we're talking about this. I don't even want to look at this slide because that slide gives me anxiety. Okay. All right. So what I like to see, it does. I look at it and it just like Boyle's law of chemistry. It gives me flashbacks, which we're not going to talk about.
About that one, since I didn't really focus on anything, all I have for my notes is the pressure of a defined gas by number of collisions. As volume goes up, the pressure of the gas decreases. That's all I have for that.
It's exactly, and it's correct. It's 100% correct. She said that only thing, you don't need to know Boyle's law. You don't need to even know the name. You need to know that when volume increases, pressure decreases.
Mm-hmm.
When volume decreases, pressure increases, which makes sense. And let me tell you why. During inspiration, when we're breathing in, okay, we're going from high to low pressure in our lungs because that allows breath to come into our body. Wouldn't it make sense that there be less pressure? Okay, let me think about this for a second. I had it all like mapped out in my brain, but then like my brain tries to think that I'm wrong, but I'm not. Okay, so when you breathe in, there's more volume, so there's less pressure. When you breathe out, there's less volume, so there's more pressure. You got me?
I think the way you can think about it is kind of like blood pressure the same way. It's like the force that's being exerted like on the wall. So if your volume is going down because your space is smaller, and therefore your pressure is going to go up. So when you think volume down, you think space smaller. And when you think volume goes up, space is bigger. And so there's not as much pressure. So if there was a bigger space, there's fewer collisions with the sides. That's how you think of it. Bigger space, fewer collisions. Smaller space, more collisions, right? Because it's kind of like the same thing like with the heart. If you have a smaller space, the heart is pushing up against the walls, right? Mm-hmm. So that's how you have to think of it. That makes sense.
Yes.
It took me a while to also come up with like a good way to explain it to myself. Because I will trick myself when I'm talking about it. My brain's like, no. And I'm like, no, yes, it is.
Yeah. So if you have air in your lungs, they're going to be expanded, which means the volume's bigger, which means the pressure. So as the volume increases, the pressure inside your lungs decrease. So if I breathe in right now, okay, the whatever the air is coming into my lungs, it's making the volume or the cavity or my lungs bigger, That's more volume. So then pressure is going to go down. Hi, Jasmine. And when the pressure goes down, then vice versa, you basically, once gas exchange happens, you breathe out, and then pressure, basically the volume of the cavity gets smaller and pressure goes up.
Yeah, because you have to have pressure to take that air out.
Yes, exactly.
Exactly. And there's more collisions going on.
Yeah.
So the smaller the space that gas is in, the more collisions that are going to happen. And it makes sense. Think of it kind of like bouncing off.
Yeah.
More collisions.
Yes. Ugly. Okay. So ventilation, which just means breathing, air moves from higher pressure to lower pressure. So inhalation, basically, I'm just not even going to talk about this stuff because, like, if you, like, I know this makes no sense to me. She didn't really talk about it, but okay, she did talk about the ribs and how they, when you breathe in, they'll expand forward. Okay, they'll be moved forward, which makes sense. Okay, if you ever think about, like, if you're ever sitting in the test and you're like, I have no freaking clue, then you have, your body, and you can think about what it's doing when you breathe in and breathe out. Just like when I was during the HESI and I was like freaking out, and I was like, okay, take a minute, let's use my own body and figure out what it is. Luckily, we have, that was the one thing that you really can do. I was cheating. I guess I could be, because you're not, anyways. But I mean, I was using my materials to the best of my ability. I have lungs. Okay, anyways. All right.
Make sure you don't do that in front of your patient. Wait, 1 second. I get it. 1 second.
All right. So the atmospheric pressure must exceed interpulmonary pressure in order to breathe in. If it does not, then you cannot breathe. An increase in volume decreases pressure, which makes sense. When you're breathing in, this decreases the pressure in your lungs, and then you breathe out, right?
Relaxing to let the air come in.
Exactly. And the diaphragm will contract and flatten, right? Like we talked about earlier. And
So
then
cavity increases.
What?
The thoracic cavity would increase once it flattens.
Yes. The volume of the thoracic cavity will increase and be bigger. It reduces pressure. So negative pressure moves the air in. Okay. There's different things that help, and the negative pressure in your interpleural cavity, that also helps bring air in. That's one other thing that kind of help. And subatmospheric, I don't know, she didn't talk about that, but she did talk about how the negative interpleural cavity or pressure that exerts on the lungs, it also brings more air in. We talked about earlier. Yeah, so we're good here. Any questions?
Wait, so you're saying negative pressure within the lungs allows more air to come in?
Well, negative interpleural pressure.
Oh, okay. Okay.
Because it's less than. What are you saying, Jocelyn? What did you say?
No, it's the same thing. She just explained me the same question I asked her because we were studying before something, and I asked the same questions once I read it, and she explained it to me, and now she's asking the same question that she just explained to me.
I'm confused.
And it doesn't make any sense that she just explained it to me. It's like you said to me, negative pressure means it's taking the negative things out. It allows air. So positive pressure,
I just got confused. I'm just eating. I'm distracted.
I just had that same question.
So do you need? So basically, I just meant the negative interpleural pressure because it's less than even so the lung pressure in the lungs. So the intercostals contract, raises ribs up and out. Forced exhalation, there's going to be more muscles recruited, which makes sense. I don't think we need to know them. It's on anatomy. It further increases the thoracic cavity volume, which allows more air in. So this is what I was talking about before. The negative interpleural pressure assists in this, and the thoracic cavity larges, ribs swing up and out, and the visceral pleural clings to the lungs, and the parietal pleural clings to the ribs. So it just makes sense if you're breathing in that there's going to be a negative. It creates a negative interpleural pressure and increases the volume of the space, and this aids in lung expansion. Any questions? No? All right.
I think someone wrote in the chat, you probably just went over it, but what is the difference between the positive and the negative? I know that negative aids in expansion of the lungs and the ribs swing up and out, but did she mention positive
Yes.
intrapleural pressure?
Yes. So the negative, like how Emily explained it to me, she grabbed this bottle and she says, okay, this is the lungs. If you put a hand to it, Emily, do you mind explaining it the same way that you said it to me?
So this is like basically the pressure, I guess, like you have the space, right? And so if you're pulling on the ribs and you're just like, you don't have any air, it's like a negative amount of space. So therefore it's going to allow more expansion. So negative space basically just means giving more room for expansion. And so then if you have a positive, you're putting force like on it, and then you don't have that space anymore for that expansion, which doesn't allow for like a better inhalation.
Okay.
Like what I got from it. That makes more sense.
Yeah.
I don't
So
know.
negative intrapleural pressure assists in expansion of the lungs. The positive intrapleural pressure assists in
Doesn't assist.
not expanding the lungs, just like
Right.
the opposite.
It can be like kind of bad in a way because it won't allow for that expansion.
Mhm.
So it can be a bad thing.
Yeah, so positive means that I guess it's in relation to the interpulmonary pressure.
Right.
In regards to that, because the interpleural pressure should always be below.
Mhm.
It should always be below. And if it gets above the interpulmonary pressure or the lungs, then it can collapse the lungs and make it so that they can't expand to allow air in.
Right. That's what I was saying, the bad part.
Okay.
Okay. Thank you.
You're welcome. You're probably like, why this is a whole. So
I know. I'm like, wait, hold up. I'm so confused. I was like, wait, what am I missing? Okay, continue on.
So this is just showing you the lungs and what they do and how the ribs go up and how the interpleural pressure is basically helping and assisting in this. And yeah, that's pretty much it. And it's, this is like at rest. So you're not doing anything basically to like go, like if you're like exercising, it's not like that. Like it's at rest. So like there's not going to be ATP that's used. It's just going to be regular respiration. You're not going to, it's just going to be like normal. And you don't use any like ATP. It's because like if you're sleeping, right, you don't have to like, you don't really have to do anything. It's just meant to keep you alive. And
You're not like forcing it.
Yeah.
Mm-hmm.
Exhalation at rest, interpulmonary pressure exceeds the atmospheric pressure. And once it does that, the lungs and the thorax recoil and the muscles relax and the volume of the cavity is decreased. When pressure increases, the air moves out, and resting in exhalation is a passive process, which means there's no energy expenditure, like I was saying before. It just means that you don't use any energy. When you do forced exhalation, there's other muscles recruited, including your abdominals, and greatly reduces volume, and it causes pressure to become much higher than atmospheric pressure, where normally it's only like a little bit, it's not much. Oh, wow. Okay. Where do I go? Okay. When you can't see the ball.
What did you say about exhalation resting? You said that just no ATP is being used, right?
No energy expenditure, which you could kind of think like energy ATP is like the same thing, but there's no. It's just a passive process, which means that it's just the recoil. Basically, it's just your lungs, just coming back to normal.
Okay, perfect.
Transpulmonary pressure differences across the wall of the lung, difference between interpulmonary pressure within lungs and interpleural pressure outside lungs. And she's going to talk about this, and this is very important because if the interpulmonary pressure, like we talked about before, if that is lower than the interpleural pressure, then that's bad. Okay, because we don't want it lower. If it is lower, or I explained it the other way, but it's the same thing. If the interpulmonary pressure is lower or if the interpleural pressure is higher, either way, it's the same thing, just said two different ways. If that's done, then the lung will collapse because it forces pressure. It forces the lung not to expand because it basically just like, no, you stay down. It's like if I sit on Jocelyn, she can't get up. I mean, it's like the same thing.
Are we coming for Jocelyn? Are we coming for Jocelyn?
Well, she was right there. I just saw her name. I was just like, the teacher knows your name, Jocelyn. Do you know that?
I bother her so much. Like that's why I said like she has to know my name. Up to this point, I will be upset if she doesn't because I bother her so much. Like she just probably dreams about me, like saying, "Is that text message, Jocelyn?" Hey.
Can we go back for a second? So I wrote down forced exhalation greatly reduces volume and pressure. Can we just explain that one more time, even though we just talked about volume and pressure?
Okay, so it greatly reduces the volume within the lung cavity because it basically forces more air out of the lungs. And it greatly increases the pressure because there's less volume, there's higher pressure because pressure and volume are inversely related. So if you have a higher volume, you have a lower pressure. If you have a lower volume, you have a higher pressure. So if it greatly decreases the volume, it's going to greatly increase the pressure above atmospheric pressure, which is what it's relating against.
Okay, so maybe I wrote that down wrong because
So
I wrote
that word pressure and volume are something related.
Inversely.
so like if one goes up, the other one has to go down.
Yes.
Yeah, I think I wrote that down wrong because I wrote greatly reduce volume and pressure, but it's greatly reducing the volume but increasing the pressure. Okay, I just wrote it down wrong.
Always, can we say it either or, like greatly increased pressure reduces volume, or we just have to put one first and the other one? Does it matter?
No, it doesn't matter.
No, I don't think so.
I mean, but you can kind of think that the
Yeah, it has to be the volume first. Yeah.
volume is kind of what's being changed, not so much, the pressure is the result, not the cause. I mean, yeah, I guess.
So it will make more sense to say greatly increased volume would greatly decrease the pressure.
Yes.
So the volume, is it the like the sizing? Like I'm kind of viewing it like that when our chest when our lungs expand or when our chest expands, I'm thinking of it like that.
Yeah.
But what about the pressure? Is the pressure like just the air? I'm just
Okay.
Yeah, right.
This is the confusing part.
Can I say that just to see if I say it right? And if I say it wrong, please tell me. Okay. So if the atmospheric pressure is higher and my lungs have to be lower, all this air is coming in. If you're putting pressure to the lungs, it's not gonna let it in. So what does the lungs do? Expands. It's just like relaxing, letting all the air in. It makes sense that it cannot have pressure because otherwise it's not gonna let it in. So atmospheric pressure is higher, my lung pressure is lower, air comes in, it's relaxed, it's expanded, no pressure, nothing. So the greater the volume it's coming in, the less the pressure, because otherwise it's not gonna work. Like you need all the air to come in. Once it's full, you need to take the air out. What happens? Our lung pressure, it's gonna be higher. The atmospheric pressure, it's gonna be lower. We're gonna put pressure in. So it's gonna be more pressure, less volume because you're taking it out. Did I say it right? Did I say it
Yeah,
right?
it made sense to me.
Okay.
It made sense to me.
Catherine, I see you serious. Did I say it right?
Yeah.
I'm ready for that. Okay.
Yeah, you did good. I mean, I wouldn't have said it like that, but you said it a lot
Say
more
it how you would say
complicated.
it. Say it how you would say it, because maybe for some other people would make sense, like to have.
Well, Emily said it about the same way as I did. If you have something, when you're talking about volume, when you expand the lungs, right? Just talking about it. When you make a cavity bigger, the molecules aren't bouncing off. The pressure is less, which makes sense. If you increase the volume or increase the size of something, the pressure on the walls of that is going to be more, right? Less.
Greater. Yes.
Well, no, so it'd be less. Oh gosh.
No, okay.
Increase.
If your space is smaller, your pressure is greater.
Yes.
Because you're gonna
The
have
way that I
more
came
force.
up with it's gonna be better.
Have more
Even
force
though it's not gonna make sense, it's just explain it for
When I can't do it anyways. Okay, when the volume increases, the pressure decreases, which can make sense because the bigger the space, the less the pressure.
Yeah,
And
you can also think about it like with vasodilation too.
yeah.
Like when you have when you have vasodilation happening, like that blood flow is flowing really nicely, and there's no force being exerted on those walls because there's a greater amount of space, right? But what happens when you constrict those vessels? Your blood pressure goes up. Why? Because there's more pressure being exerted on the walls. So you can think about that like the same way with the lungs. If you have a smaller amount of space, you're going to have more pressure being exerted on those walls because those molecules are trying to push out, right? But they don't have anywhere to go. So that's going to build up a lot of pressure in that space. But what happens when you expand that space? You have all this space going on, and now the molecules are slowly bouncing off, but they have a greater amount of space to do it. So that pressure now has decreased.
yeah, because they're having more space for them to.
Now there's more space. If you relate it to vasodilation and vasoconstriction, it's going to help you a lot because it's the same concept. Smaller amount of space, greater amount of force. Bigger space, less amount of force. So you can physically think of a vessel getting smaller, and then you're like, oh my God, pressure is increasing. So you can think about it like that.
So once pressure is increasing, what does that change in blood pressure? It does that have anything to do or not necessarily? That's like
Yes,
heart.
if the vessels are constricted, you're going to have a higher blood pressure because blood pressure is basically how much force is the blood exerting against the walls of the capillaries or of the vessels.
Is that coming up in somewhere there or not? Like the same thing that you said? Okay.
That's just blood pressure, like part 2.
Say it again.
Okay, so blood pressure is basically how much force is the blood exerting against the vessels in which it's,
how much blood?
What?
How much blood or pressure?
Pressure.
How much pressure blood is exerting in the walls?
Against the walls of the vessels.
I have a question. Is the test going to be also in blood pressure as well? Yes, like the second part?
Yes.
Yeah.
Okay.
Part two.
Part 2. Okay.
All right. Okay. All right. Are we ready to move forward?
Yeah.
So this is showing you, I love this diagram. I don't particularly, what?
I said me too.
Oh, I was like, I thought you said ew. I was like, okay.
No.
For everyone. Okay. So at rest, normal atmospheric pressure is 760 milligrams per mercury. Interpulmonary is 760 milligrams per mercury, and interpleural pressure is 7. Wow, why I keep saying set? You guys gotta correct me on my freaking sayings. 756 milligrams of mercury, and it's a little bit less than pulmonary pressure, and that's good, and that helps with respiration, and that also means that we're not, our lungs aren't collapsed, so we like that. Okay. So in inspiration, basically the pressure in our lungs goes down and the atmospheric pressure obviously stays the same, and it allows air to come into the thoracic cavity. And when it comes into the thoracic cavity, gas exchange happens. This stays, it gets a little bit more negative, but it stays pretty much the same. And the reason why it gets a little bit bigger is because the cavity gets bigger. So the space between the ribs, where the parietal pleura is attached to, and the visceral pleura is attached to, which is the lungs, gets bigger. So that would get a little bit, the pressure, well, wouldn't the pressure go up? That doesn't make any difference.
No, pressure would
Increase because it gets bigger. The volume gets bigger, the pressure will go down.
Down.
Oh, yeah.
Yeah, okay. I did it. I just said it. Okay.
Wait.
This is hard.
I wonder, which I probably shouldn't say it, but I wonder why at rest the atmospheric pressure is 760 and the interpulmonary pressure is 760. So no, there's no air moving. So how we are
That's
not
passive.
having any air moving and then just being alive? Because
It's passive. It's passive.
look at Jasmine laughing. Girl, I had to ask it.
It's passive. So it's like you're not using the force to push to breathe in. It's kind of just like,
So there's still air coming in, right?
yeah, it's just passive. It's not moving. It's just like when you're sleeping
Okay.
or when you're sitting here right now. Now, if you went out for a jog, you're going to be forcing that air in and forcing that air out. And that's what's like the inspiration and the
I'm
expiration.
sorry for stopping this, but I had to stay in. I better stay
So
in
I
now.
think,
No, that's a good question though, Jocelyn, because I was thinking the same way.
I was just
wait.
like, how am I alive? And then no air moving. So
It's when you're not breathing. It's when you're not, like, okay, so think about this. When you breathe in and you breathe out, you stop breathing for a second, and then you breathe. Right? You like, there's like a little bit of space between your last breath and the next breath. You're not constantly breathing. You're not like, right? You're like, there's like a little rest part. And that's when the pressure is the same. It's like
that little, yeah, okay.
Talking about breathing and like all that stuff, I'm like sitting here like focusing on my breathing, and I'm just like,
yeah.
like I can't.
Olivia, I think, okay, so for inspiration,
Excuse me, Catherine, please and thank you.
what?
Oh, sorry, Olivia. Why did you change that? Like, just change it.
Because it's my government name.
Oh my goodness.
Jocelyn, you're trying to get me in trouble over here with the
I just got
teacher.
confused.
Me cago en la mierda, te mato.
With the teacher.
Trouble. Trying to freaking get me in trouble with the teacher over here.
Sorry,
I'm
I
not
got
a
confused.
teacher.
I missed last class. I'm sorry.
So I think, okay, so the thing is that, so this one's confusing with the inspiration, like why the intrapleural pressure goes down. And I think it's because your space is increasing because the lungs are taking over that space.
Exactly. So your entire cavity is getting bigger, including your lungs. So
I think we're confused.
the space between the ribs and the lungs
Mhm.
is bigger. So the pressure is less because the volume is more.
Yeah.
Volume more, pressure less. Okay.
Yeah. I mean, both the intrapulmonary pressure and the intrapleural pressure are less than the atmospheric pressure.
Yes, and that's during inspiration. And expiration, then basically the pressure goes up because you're basically breathing out, and the pressure is going up, and both the pressure of the interpleural cavity and the interpleural, I guess, cavity and the interpulmonary cavity, or your lungs, are getting smaller, and they are having more pressure so that you can expire your air. Okay, guys, this is where we get to talk about diseases. I know you're so excited. I know. I hope.
I don't even think I've gotten to this yet.
Okay.
Yeah, I didn't
So,
know yet.
okay. So we're going to talk about two things, and this is very, very important because we're going to have lots of questions on this. So we gotta know this. Compliance and elasticity. Now, compliance has to do with what?
Age.
Of expansion.
Ease of expansion.
It has to do with age.
Age.
God, having to do with
Okay.
age.
Oh,
Jax,
age. I thought you were saying H. I was like, what
no,
the
he
H?
said age. Okay, Jack Saint and Morgan, I think it was. Yes, you're right. Okay.
Hello, what happened to me?
Age, that has nothing to do with compliance.
Yes, as older you get, the less compliance you have.
That's true.
I can also
So,
You go defend her. You defend her, Peterson.
thank you.
defend her to death. But this is see right here, factors that reduce wow. Right here, pulmonary is that age? Does it say age?
No, but it's gonna come out.
Nope.
Like she said
Nope.
it. Yeah, she said it. Remember the story about her and her husband? How he said, "Okay, beat that."
Oh, Jocelyn,
Yeah,
that was
it's
about pulse
like-
pressure. I love you.
That was about pulse pressure, I think.
And then
But
she
is that
also
compliance too?
Jocelyn. Then she also talked about how he has severe asthma, and that's why he has poor compliance. Well,
So compliance, nothing
no,
to do with
no.
age.
no, not really. No.
So what was the right answers?
It was about elasticity, but okay. So compliance is easy expansion. So it's basically how well you can take in air. How well do your lungs expand and stretch?
recoil. And
Take
recoil.
and
Got it.
no, not recoil. Don't look at that.
Oh,
It's ugly.
damn.
That's about elasticity. Okay. That's how well we're gonna talk about it in a second. We're gonna talk about it. I promise. Okay.
Little by little.
Little by little.
Little by little, exactly.
So compliance only expansion.
It's
Yes.
important for inhalation too.
Yes, exactly. So it's important for how much air that you take in. There's two factors that affect this very much so. One is pulmonary fibrosis, which is basically if you work in a coal mine, okay, or places where small particles can get into your lungs, it can cause scar tissue. And not like smoke and stuff like that. That's not what that is. It's like from like coal, and there's a bunch of them, but it basically like black lung coal, and it basically causes scar tissue, and it reduces compliance or your ability of your lungs to expand and stretch to take in the air. Another thing that can cause this right here, we talked about earlier, positive interpleural pressure. If there is more pressure in the outside cavity of the lung, then this greatly reduces compliance by collapsing the lung. In fact, that it can't take in or stretch because of the pressure. So it can't breathe in, and that reduces compliance almost entirely. You can't take in any air with that lung. Hopefully you have another lung. Hopefully you
remember about the pulmonary fibrosis? Did she said anything about it? Like
yes.
So what was that? The pulmonary fibrosis.
The pulmonary fibrosis is basically in people who take in particles that are very fine and their lungs start to scar. And it has to do with things like asbestos and coal, but not in smoking or anything like that.
Does that have something to do with the celiac not working,
Nope.
like not getting that particles and it's getting to the lung?
No, it just means that those fine particles can't escape the filtering. It escapes the filtering mechanism because they're smaller than 6 micro something. Like,
Millimicron.
they're very small, so it escapes that
And
that filtering
it's
mechanism.
causing just that tissue to scar.
Yeah.
Yeah.
It's basically like the same thing in your liver cirrhosis. It's the same thing. It's a collagen it's basically scar tissue. It turns into scar tissue, and if it's scar tissue, it doesn't work anymore. And so it cannot expand in this case. And positive interpleural pressure. Okay, so this is just showing you that in different situations, so this is what I was talking about before, the pneumothorax, that's the collapsed lung. And that's what happens when there's the interpleural pressure is positive. And also in fibrosis, compliance goes down because it can't expand, right? So this is even showing you the pressure. As pressure increases, the lung volume should decrease. Yeah. But here, why does it show that it's both going up? That doesn't make me happy.
Okay. So
So
what I have for that, it says the higher the volume, the higher the compliance.
Okay, I'm guessing this is showing you the pressure going down. I don't know. We're not gonna look at that.
that's transpulmonary pressure. So that's the difference between the pressures. That's not like the actual pressure.
Yeah, it's the compliance.
It's the
So the higher the volume, the higher the compliance.
Okay.
Oh, I hate this
And
pressure.
the lower the volume, the lower.
This whole pressure volume thing has my brain so messed up.
All right, so let's talk about the next thing. The next thing is elasticity.
Sorry.
It's
Okay.
basically the lungs' ability to recoil. So after you breathe in, wait, I can't even breathe in. And then when it goes out, that's recoiling. It's going back to the same original size after distension via the inspiration, okay? And the lungs have elastin proteins, basically, that make it so that they can stretch during inhalation and recoil during exhalation. And basically, what mainly affects, or like one of the biggest thing that affects elasticity is COPD and things in that, like asthma, as
Emphysema.
Pneumonia,
emphysema, pneumonia, and
blockage of
chronic,
air.
chronic bronchitis and blocking of air. So an pneumothorax would also make it so that the lungs cannot expand, and of course they couldn't go back to normal because they're just like sitting there like you can't breathe. So it's bad.
What did you say that affected steel or what? No, you said something.
What?
You said something that affects elasticity, and you said something, but no emphysema or pneumonia, like the first thing that you said.
COPD.
COPD. What's that?
Chronic obstructive pulmonary disorder.
Mm-hmm.
And all the things that I described are all obstructive diseases.
Chronic what?
Chronic obstructive pulmonary disorder. I think that's right.
Yeah, it is.
Mary.
Buddy.
And all of them, what do? They affect elasticity?
Yes. So they affect the lungs' ability to recoil or bounce back, like exhale.
Okay. Affect recoil. Okay, perfect. Got it. Thank you.
So this is showing you what a pneumothorax is. So basically this is the interpleural space, and it's exerting pressure on the lungs so that it cannot expand and it cannot do anything. So it just sits there, and this guy's not happy. And he said this not happy guy. And then once you put a chest tube in and allow that air or blood or whatever is in there to get out, then guy's happy. Well, he's not happy. It hurts, but it's called electasis or whatever the hell. Okay, so fun thing, you get to come back to this. I know some of you weren't here, so I'm gonna give you a rundown. All right.
Olivia, can I ask like a quick
Yes.
I like somebody like called my phone and like Zoom automatically muted. I just wanted to know if we needed to know anything for the elastin proteins.
No.
No, like high elasticity, like none of that.
Yes. So like know that the lungs have ability to expand and can like recoil very easily.
Okay, but I don't need to know those elastin proteins.
No, there's none she really described. I mean, if she ever asked a question like, does the lungs have elastin proteins? Well, that makes sense. Elasticity. I mean, you could kind of defer that yes, they do. If she ever asked that, but she didn't say that she was going to ask about this, but she is going to ask about this.
Yeah.
So
just know that lungs have that ability to stretch and recoil
very easily.
Very easily. Okay.
Their job. Is their job.
Okay.
They're meant for it. They're ready for it. You need to breathe. They got you. They're your homies.
I think Jasmine had a question, then I need to ask something because I'm
All right, yeah, spam, Jasmine, let's go.
Okay. I feel like it's a stupid question, but is the pneumothorax, is that the positive intrapleural pressure, right?
Yes, ma'am.
Okay. I just needed a clarification. Thank you.
You're welcome.
So the pneumothorax is positive, and then the re-expanded lung, it's negative? Or both are-
Negative?
Yeah, it should be negative. Negative. You always want negative.
So
Okay.
the re-expanded lung, it's negative, the pneumothorax positive.
Yes,
Okay.
ma'am.
Perfect.
I'm still confused on like the elasticity and compliance and like why emphysema and COPD like elasticity is more important than the compliance.
So this is why I'm going to get to that.
Okay.
It's tied in with this subject.
Okay.
So that's what I'm talking about next. Surface tension. We don't like it in this case. It basically the water hydrogen bonds, and that's why it allows this paperclip and this bug to sit on the top, because these hydrogen bonding, so they can just sit on top and not go to the bottom, and it kind of just like sits on top, and that's what it does. But in the lungs, it has water in the alveoli. And you'll see this later, and it's true. There's more water in the alveoli than in the atmosphere. And if you have water in the alveoli and you have such a small area, right, such a small place, and when you exhale, that gets even smaller. If it gets smaller like that, then these hydrogen will bond and cause the alveoli to collapse. That's not good. We do not like that. And that is what happens in COPD. Not because of surfactant, okay, which aids in helping this, but because of the fact that they have destroyed some of their alveoli walls, and the bigger it is, the more surface area, surface tension, so it will contract a lot easier. It's really bad. That's why during expiration, the alveoli gets smaller, and if it gets smaller and the hydrogen bond, then they collapse. And that's kind of what happens in COPD. And that's why when they can't exhale all their air and it gets trapped in their lungs and they can't. It's kind of why. But we're going to get into that. I don't want to
Sorry to ask again for it because I already asked for that. So COPD is chronic obstructive
pulmonary disorder.
And then you said what happens with that, it gets so small that it lets the water molecules attract each other and the hydrogen.
No, it doesn't get small. So the alveoli walls break down, and I'll show you examples of what it looks like. And they become very, right here. You see this one? This is an emphysema. You see how the alveoli walls break down? Basically, they get destroyed. And then there's alveoli like this that are basically, they are like this. And then once they get smaller, the surface tension, the hydrogen bonding will basically collapse the alveoli. And that's why the air gets trapped in there. And then they can't breathe out all their air.
Okay. So what happens, that's the COPD as well, right?
Yes. COPD is it's an umbrella term. Excuse me.
Okay, so
Yeah,
COPD,
I was just about to say that.
it just breaks the alveoli walls. They break down. So the walls, the alveoli, they start getting smaller and smaller, and then it traps air in, and then it doesn't let it out. That's like the main thing that happens.
Yeah, they get thinner and they break down, and yeah.
And then they trap the air, and then you cannot exhale.
Yeah.
And what does that cause, other than obstructive in that?
High CO2 levels.
I remember that.
You can't breathe.
You can't breathe out all your air, and they get barrel chested, and basically the only thing that's really controlling their chemoreceptors aren't working, and they basically are their blood oxygen PO2 levels, which we're going to explain all that, are going to be the ones that are in their peripheral chemoreceptors are the only things that are monitoring the amount of oxygen in the blood. So really they could be like walking around being like 60% or like 65% oxygenated, whatever, all the time. And basically they
Receptors cannot work, right? The baroreceptors will not be able to work.
chemoreceptors. Baroreceptors have to do with pressure of the vessels, and chemoreceptors have to do with the amount of basically hydrogen or CO2 and oxygen in the blood. PCO2, PO2, and H plus.
Okay, chemoreceptors have to do with what? With
Monitoring the pH of the blood. Okay. I'm gonna get to it though, but
you're
it's
gonna
like
get there? Okay.
yeah,
that's fine.
yeah, 100%.
Olivia, I'm sorry, I don't understand the whole water molecule thing with COPD. Are you saying that like I don't understand the water molecule thing?
Okay, so when the basically the surfactant is still there, but the walls of the alveoli get broken down, and if they get broken down, then the basically the water when you breathe out, your alveoli contract, not really so much contract, but they get smaller, and when they get smaller, then the surface tension or the hydrogen bonding of the water molecules will cling together and cause the air to be trapped and for like your alveoli to collapse.
Okay, so the surface tension increases because the walls are thin and you have that wall breakdown in the alveoli during expiration.
Yeah, and a lot of the air will get trapped in the alveoli.
Okay. And so this causes the hydrogen molecules to attract each other because of that wall breakdown.
Well, it is that way.
What they do, right. But because, okay, I think I get it.
Because the alveoli walls are broken down, it just it's just like all messed up. So basically I don't know how to explain it so much so is like the air will get trapped because it comes in but it can't get out. And
right.
And if we didn't have this thing called surfactant in normal people, then then the alveoli would still collapse after every expiration.
Okay.
But they collapse very commonly in people with COPD and cause the air not to get expired because they're trapped. So they can't get out.
Okay.
So surfactant is only in healthy individuals, and that what causes the alveoli not to.
I don't think so. I don't think it's only in healthy individuals. I think there's still surfactant in people with COPD. I just don't think that it matters anymore because they broke down so many walls and it's just so broken that it's like.
Got it.
Like I can't do it. Like I try.
Right. Okay.
And I think it's more about how like the walls are broken down, so it can't really assist well in gas exchange, and how because there's less surface area and they collapse much easier because of the fact that there's like it's just not conducive with like expanding. If it gets closer together, it's just gonna collapse because there's just it's so. I don't know how to explain it. I'm guessing she'll explain it probably if you asked her. She'd explain it a lot better and more clear than me. Because
I just wanted to make sure that it wasn't only in like healthy individuals and.
No.
Okay.
I don't think so. She might know. She might say it is only in healthy individuals. She might say that it just those cells go away. Which would, I mean, a lot of cells will go away because of destruction. You know what I'm talking about?
Right.
That might be a cause, and there's so little of them that maybe like when you do smoke and stuff that those cells do get destroyed a lot faster because, it just makes sense,
Yeah.
So that might be one reason. I don't know. Yeah. I can't be like, yeah, I know. Like, I have no idea. Like that.
I don't think it's important. I think I'm just like curious, like if it's present or not. I could look it up on Google.
Yeah, you could. Sometimes I've looked something up on Google and I actually understood what it said, and I was like, oh man, oh gosh, such a such a thing. I was like, wow. Anyways, okay, so fluid in alveoli is important for gas exchange because without it, you couldn't really. It just assists in like the lubrication, and without any lubrication, it wouldn't be good with the gas exchange and all that stuff or whatever. There's thin layer. You need thin. Thin is good because if you have thick, then this would inhibit or like I don't know the correct adjective, but it would halt or I don't know. It would not be as good for gas exchange. And water and lungs will secrete and absorb to keep the layer thin, which makes sense. Water molecules like each other and exhibit surface tension, which is what I was talking about. Two wet sides would collapse alveoli with each expiration, which makes sense because the hydrogen bonding, that's what it's caused from. Because when they get close to each other, like, oh, hey, you're my best friend, come over here, like we gotta talk, and then they collapse. But there's this wonderful thing that we have, it's called surfactant, and surfactant is a soapy film that's secreted into the alveoli by type 2 alveolar cells, and it's interspread between the water molecules, and it reduces the H bonds between the water molecules, which is the hydrogen bonding, and reduces the surface tension to negligible levels, which means that there's very little, and collapse is avoided. As the alveoli get smaller during exhalation or like breathing out, then the surfactant is concentrated and it allows the alveoli to easily reinflate and it doesn't cause them to collapse. And this I wanted to show you guys is, so this is normal. It looks normal. There's like little areas. It's very nice, very beautiful. It'll thin layer. Excuse me, sorry. There's thin whatever walls so that a gas exchange can happen, and they're not too big and they're not destroyed and they're looking good. Okay, this right here is pneumonia. It could be pulmonary fibrosis because you see these cell walls, they're very thick. I'm guessing they're cell walls, flappy, what they're called. Well, anyways, they're walls and they're very thick, and we don't like that because if they're thick, then that inhibits or like stops the amount that can be, I guess, absorbed, the gas exchange. It inhibits that, so we don't like that.
Olivia, can you, oh, sorry, keep going. I'll ask you after.
And then this is what I was talking about before was emphysema and how see how they're greatly impaired. The walls are greatly impaired, and that could also be because it said that the they're on the walls. Where was that? I don't know. It was somewhere. Okay, so it's on the wall of the alveoli. So it makes sense that if the walls of the alveoli are destroyed, then maybe some of these cells are also destroyed with it. Got me? Yeah, maybe that's why.
I have a question.
Yeah.
I missed this little part in the surfactant slide. It says as alveoli get smaller, exhalation and surfactant concentrated. What was that again? Like,
so when you breathe out, your alveoli will get a little smaller, and when they get smaller, the surfactant will become concentrated and allows so that the alveoli cannot collapse, and they're easy to reinflate, which means you can breathe in again.
So it doesn't allow the alveoli to collapse. Okay. Thank you.
Nope. Okay, so premature babies, okay, as you can imagine, they lack this. Makes sense because surfactant only accounts for like 3 to 5% or something really small of the amount of cells in your lungs or in your alveoli. Okay, makes sense. If you have a fully developed baby, then they would have these cells, but because it takes a while, right? Because it's one of the last things made, is that the correct word? I don't know. Develop. I don't know. How would you say it? I don't know.
Develop, yeah.
I don't know, yeah. And preemies or people like really young babies lack sufficient surfactant, which makes sense because these cells aren't developed yet, because 95 to 97% of the cells are alveoli cells. So like that's the last thing that, you know, babies are developed. That's right. Woohoo, I did it. Okay. And this is bad because the surface tension, or what we talked about before, the hydrogen bonding in preemies, if they don't have surfactant, then their alveoli collapse, and this causes respiratory distress syndrome. And it's very common in preemies under 28 weeks, and it's kind of common in preemies under 34 weeks. Okay, so if you know that the baby's going to be delivered early, then you can kind of think that, well, steroids are given to the mom. Makes sense because steroids assist in basically helping develop the lungs and develop and help that. I don't know. I guess that's right.
So once you know you're delivering before time, just give them the mom steroids, and that will help that surfactant. Baby.
Stimulate.
Yeah, it'll help the babies form their lungs faster. Like the first thing you're gonna do when you have a premature baby is give steroids to the mom to speed up the process of developing the lungs. It's like the first thing you do.
And what if they're born and you didn't have time? Like there's no way for you to know, would the baby die or?
No. Okay. So
Die.
they would not die. Okay. So I'm talking out of turn. I went to one seminar. Okay, I worked and volunteered at 2 hospitals for a long time, and I got to know the nurse manager really well. She's actually part of my family here, that I live in Florida, and so she took me to the seminar, which, you know, was really, really cool because it like basically was talking about premature babies and all this stuff, and it talked about surfactant. And of course, I had no idea what surfactant was then. Read a little bit about it, and you know, I figured out what it was, but they can now synthetically give the baby surfactant via this way where they literally like put it into their lungs so that the baby can have surfactant and be able to, I mean, it's not like a foolproof way, but it's one way, and they can intubate and they can do a bunch of stuff like to help, like, so there's different viability, which just means if a baby can live by itself, not, you know, with help, obviously. They said during the thing, it's like down to 20 weeks.
Would it develop eventually, or like once it wasn't developed, it won't?
Yeah, it would.
They will develop it. They just need a little assistance at first.
Okay.
And then they keep giving them steroids to develop that,
And
develop
if
it
fully
themselves.
developed, they should work back to normal. Like if it.
Yeah, they should. They just need like treatment until they can develop it. That's why they give them the steroids. They'll still give them steroids to help them develop the lungs since they're not inside the mom anymore.
Yeah, it's just like, okay, so like there's different things like when a baby is born, there's different parts of the body that are still developing. Like, so over time, just because they're not like in the mother, they can still develop certain things. Like there's neck. The neck is, I don't know exactly, but there's something with the neck where when your baby's born that they don't have movement in the neck, that they can't move their neck, so it's kind of limp. So you always have to hold the neck, because if you don't, then they could break it. And there's like the anterior fontanelle and the posterior fontanelle. Those are things in the brain which are like separated the skull, where it's not closed yet. So over time, those will close. And I think like one is like 6 months and another is a year. I think the anterior fontanelle is like a year, or is it the transverse? I don't know, it's something. And the posterior is like a year or something. But there's different things that develop later in life, and you know, lung function, and also the the esophageal sphincter, the lower esophageal sphincter is not fully developed in a normal delivered baby, so that's why they have colic, or they have
That comes out.
So they can't, you need to burp a baby every time after you feed them so that they don't get gas or it's like a different thing. But I don't know, I've never had a kid, so, but I know that that's one thing that is not developed yet. And there's probably a whole bunch of other stuff, but over time it will develop. And that's amazing, right? So that viability is down to 20 weeks now that they've saved kids, but you know, there's obviously the brain is not fully developed and it can't there's been cases of some babies being fully cognitively amazing, everything's amazing, and then there's obviously major deficits in others because the brain functions not at 100%, and there's obviously different things that the mother gives to the baby during growth and you can't give them when they're in an incubator, whatever. Okay. Oh, and also liver function. And in many premature babies, they have to give you the UV light so that they can, you know, start the liver or basically convert the bilirubin or whatever the hell. You know what I'm talking about.
The yellow thing.
What?
What's the name of the yellow thing?
Oh,
Jaundice. Jaundice.
And it's because they can't secrete the bilirubin. Right.
Do we need to know that?
No, I'm so sorry. I'm so sorry. I hope you didn't write that.
We're just
No,
talking
I
about
was
things
like-
that like babies don't have developed yet. All the problems that they have when they're
Oh, I was like UV light. I was like, wait, shit, fuck, what? I was like, oh my
Can we
god.
like rewind?
Yeah, I was like, wait, go back.
No, we were just talking about different things that babies don't have when they're born.
Well, maybe we need to review those.
And
I'm pretty sure we have to review those for the anatomy part because anatomy is accumulative, and that we gave it in anatomy. The jaundice, the liver, like how it wasn't developed. So we might as well just refresh it here because eventually we're gonna have to learn before the test. No, not learn, but like review it.
well, the jaundice is a buildup of bilirubin that isn't excreted, and it can happen. There's many ways that it can happen. One way is the most common way in adults is because liver function is greatly inhibited, and they don't have a functional liver. And some does get excreted in the kidneys, but not enough that it won't build up. And also bilirubin in babies, they don't have mature livers, so that they cannot synthesize the bilirubin into the water form so that it can get excreted. And so how they fix it is by UV light, and they figured out that UV light is able to convert bilirubin to its water soluble form and allows it to be excreted.
And then how do we see it? It will be in the whites of the eyes. It will be yellow, then the nails and stuff
Yes,
like that.
ma'am. Yes, ma'am.
I kind of remember.
You did. Yo, I'm not going to talk about that. Never mind. All right. I was talking about the paper, but you're not even a part of it.
Listen, you just started with the Joe, and that just caught my attention. So I'm ready for that. You're like, yo, I'm like, wait, this is interesting.
Okay, I'll pause it real quick. Oh, she said, you're not supposed to see that. Oh, I'm sorry, Morgan. It was supposed to be private, but it's okay.
It doesn't matter.
All right.
I missed
Nothing to hide.
So it's just showing you the normal alveoli and the collapsed alveoli regard, like in the surfactant. When it doesn't have surfactant, then it collapse and drop the air, and it's not good. Okay, good. Okay,
Can you explain that one again, please?
the alveoli.
Because I know she said so. Like, I don't know. I'm not sure if I understand what's happening on the collapsed alveoli.
Okay, so basically, where is it? Okay, so basically, there's water inside the alveoli, and when water comes closer together, like in exhalation, when it comes closer together, then the water tends to want to like cling together.
Yeah, the hydrogen ions bond.
Yes, and if it does that, then that will collapse the alveoli.
And what surfactant does is like it doesn't let them bond.
Yes, exactly.
Okay, thank you.
Welcome. All right, so spirometry. All right, so what we're gonna do is we're gonna look at this chart because it's my favorite chart. I love this chart. It's amazing. Okay. I would suggest you all get flashcards and you just study them because it's not complicated as long as you like write it down. I feel like if you write it down on cards, it's going to be so much simpler. So inspiratory capacity, any capacity is two volumes together. So inspiratory capacity is basically the tidal volume when you inspire and breathe in normally, and in the inspiratory reserve volume. So it's those two together. And those two together is the inspiratory capacity, or basically the range in which you can inspire. Okay, so you can be regular, or you can breathe in really a lot and expand the lungs even more so. Okay, as shown here.
The capacity is to what?
We basically the amount or the range in which the lungs can expand or breathe in. So it's like if I was like just normally breathing, but also your inspiratory reserve volume, which is like when you're exercising, you're breathing in a lot more. So it's me breathing normally plus me breathing in as much as I possibly can. So it would be like from here to here.
Isn't that also the same as forceful inhalation?
Yes. Yes.
That's what it is? Okay.
Yeah. Yes. It's the amount in which your lungs can forcefully inhale and not forcefully inhale. It's just like together. It's like just basically the amount that your lungs are capable of inhaling, and vice versa. So the tidal volume is basically how at rest your lungs expand and like inspire and expand, and you know what I'm saying, like just normal respiration.
So someone with pulmonary fibrosis, they will have trouble in the inspiratory reserve volume.
Yes, ma'am. Well,
And
they'll have trouble in the tidal volume too.
Yeah, I guess.
I mean, they'll just have trouble normally inhaling.
Inhaling. And then emphysema would be on the expiratory reserve volume.
Yes, ma'am.
So the inspiratory reserve volume is the amount that your lungs are capable to exhale, right?
Yes, like when you're forcefully inhaling.
Okay. So no exhale, it will be inhale. The amount that your lungs are capable to inhale, nor exhale. Right? If it's inspiratory reserve volume, inspiration, it's just breathing in.
Inspiratory reserve volume is the amount of volume that you're capable of inhaling.
Inhaling, okay.
When you're forcefully inhaling, when you're using your muscles and your entire body to inhale. Like if I go, like I can feel myself using my muscles to basically expand my thoracic cavity and allow more air in.
Okay, perfect.
Okay. And so expiratory reserve volume is the amount of basically the amount of air that you can get out when you're forcefully exhaling.
Yeah. And the residual volume, no matter what you do, air cannot be taken out of there.
Yes, residual volume is always going to stay in there. Nothing you can do about it. Mm-hmm. It's to prevent lung collapse. If that's not in there, you're fucked. Pardon my language. All right. And that's recording, guys. Love that. And
that's to prevent lung collapse.
Yes.
So that
I
has
wouldn't say that.
nothing to do.
I wouldn't say that. I would just say that air is always going to remain inside there because you don't want there to be no air inside there. I don't know if that just sounds pretty, but I guess, I mean, I'm guessing that's what it's for because
And if you try, you can, because I've tried it. Like when she says try to like exhale out of it, you start coughing, and then automatically you're gonna try to breathe in. So it's always gonna have some little air. Because you try like exhale completely forcefully, and then you start like coughing, and then automatically your body's gonna make you inhale. So
Because
there's no way you
I
can.
thought she
remember.
specifically said it was left there because it's to prevent lung collapse.
all right, bet. Cool, I was right.
Welcome, Mandy.
Okay.
I don't see you, but I recognize your voice. Girl.
I know, I didn't realize you were here, Mendy.
Yeah, I didn't see her. Oh, here.
Hiding.
To prevent lung collapse.
Yes, ma'am.
Thank you.
I was right. I'm so proud of myself. All right. I didn't think I was right. All right. So vital capacity is basically everything that you can possibly inhale and exhale. Just all of it.
Which one's all of it?
Vital capacity. Vital capacity is a summation or basically the sum of the inspiratory reserve volume, the tidal volume, and the inspiratory reserve volume all in one.
Oh,
TD volume.
everything. Sum of everything.
Is the whole point of this graph just to talk about the spirometry? Like,
Yes, ma'am. Yep.
yes? Okay.
Good.
You don't have to listen.
I didn't have to
Tune out.
read
You can
it.
tune out if you want to. I am going to talk about why this is clinically important, but you can tune out until that point. I'll get to it in a second.
Wait, Olivia, this is off topic, but did you have Gallo for lab as well as lecture?
Yes, ma'am.
Did you have him for anatomy too?
Nope. I didn't get him.
Oh, okay. Yes, like draw this chart, the entire chart, and we would get a grade for it, and we could use it on our final. I literally had to draw this whole chart.
Yo, that's
Did
lit.
you guys go to NSU for your first 2 years?
No, we went to Palm Beach State.
Oh, okay. Yeah, I have yet to meet somebody who was at NSU. And
There's
went
been
into
2
the-
people so far.
Yeah.
I've met 2 people. It's amazing to me. Everybody
Yeah, I don't know.
transfers because they were broke.
I was gonna do it, but I was like, no. I'm not gonna pay that money. I'm not gonna pay that.
Apply for scholarships.
I did. You still don't know.
Applying. Keep on applying. I applied to 18 of them.
I did. I applied to a lot. I got like 3, which was amazing. Because if you apply to the local ones, you'll get them more often than the international ones, or like the national ones or the state ones.
Where do you find the scholarships? At the NSU website?
Yeah, I would just call your advisor and ask them. Like I applied to 18 of them. 18.
From NSU that you found at NSU?
All of them are there, and there's one that just came out. I think they tell Emily last time that one you only apply to one, and they send it to hundreds of them. So you only apply once, and they send it. And that one I didn't have. I had to apply to one by one. So now there's one that you apply, and they send it to 156 to 286 scholarships.
Wow.
So that's amazing.
Oh, which one is that? Yo, Emily, send that in group chat, please.
It's like
Try to see if you have it, because that was a long time ago.
Franco send it to me. I'll ask him for it again, and I'll send it to you guys.
If anything, we could send it to the chat. We're in the chat for
It was so long ago.
Yeah.
I have to look at it.
All right.
Yeah, I think I spoke to Edward, and he said now the scholarship applications will be due in March now for like the new year, like August 2021. So he said the scholarships will like usually be due in March, and you'll hear back like in April or May.
So don't procrastinate on that because they pay you full and you don't have to pay back.
Mm-hmm.
All right.
Yeah.
So
What's the name of that scholarship? Just sorry, I don't want to interrupt.
We don't remember because it's like long time that we found out
Oh,
about it. But if you're in the chat for Fort Lauderdale, we can send it as soon as we find it. Or we
Yeah.
can ask Edwin and then just send it.
Thank
Yeah,
you.
NSU students applying. They're gonna be like, what?
That's
What's
fine.
going on?
whatever.
It says they don't-
He said it's not limited. So it's not like one gets it and that's it. There's a lot of them. And just because you win it, there's like from our class, I think, not our class, like our school, it's like only like what, 23 students or something. It's 5 people applied and they all got it, I think.
It's just like annoying because I got the NSU like Dean Scholarship, which covers your tuition like for nursing school, but it's only for people who already like go to NSU. And I was just like, why? I was like,
No,
why?
because you should
They're like,
get
yeah.
No, because you should get it because I talked to the person there because I thought I should get it, but I actually didn't. And I was really pissed for a while and I still kind of am salty, but they said that if there's only 2 exceptions. One, if you were previously at NSU, like you just said, or 2, you were going to a campus that is not Fort Lauderdale. If you were going to the Miami campus or the Fort Myers campus, when you can't talk.
Why the exclusion? Why are you being
so many
for being in Fort Lauderdale?
There's so many of us. They don't
Oh,
want to give it to us. They want to make that
No,
money.
I didn't go. I didn't go to NSU. That's why they didn't give it.
No,
to me.
no. You don't have to. The 2 exclusions, one is NSU and the other one is if you go to either Miami campus or Fort Myers.
so they're excluding the people from
No,
Fort Lauderdale because
wait,
too many.
I'm talking to Emily. What did you say?
wait. So for the NSU Dean Scholarship?
Yeah. Or it's like a transfer scholarship. It's the same one.
Yeah, because the NSU Dean Scholarship is for people who are like going into like the nursing program. But they told me it was like an entry like scholarship and you get it like only when you're entering the program and it's only for people who already go to the.
There's a transfer one too, and that's the one that I wanted to get. But they said to me, you're able to get this, but because you're going to the Fort Lauderdale campus, you cannot. If you were going to the Fort Myers campus or the Miami, then you could. Yeah.
There's one that I'm gonna totally recommend. Apply to Nurse Corps scholarship. That's the best you could get. Nurse Corps. Write it down. Memorize.
I'm like patiently waiting for that one to open up.
Nurse Corps. They pay for full scholarship and they pay you every single month for your bills so you don't have to work.
Repeat that.
Nurse Corps. CORPS. Nurse Corps. And then if you for the website, it's hrsa.com, I think it is. Let me see, I have it here. You apply for that one. Apply. If you don't get it, apply as many times as it opens. You're not. Oh, it's hrsa.gov.
Write it to the chat, please.
Give it to me.
Can you send it to the chat, Jocelyn?
They gave it to you?
To the chat.
They gave it to me and then they took it away.
Because you have to be freaking on that, man. You have 5 days. Once you get it, you have 5 days to reply to accept it. Otherwise, they take it.
No, they took it. Like I called them and they were like, "Oh, we're gonna be taking this off of your thing because you don't go to Nova. Like you didn't."
Sorry. HRSA.
They said, "Hey, like I know you got this scholarship, but you can't use it for the nursing program because you don't go to NSU. Like you're entering NSU." But I'm looking at the transfer scholarship right here and it says Dean Scholarship.
Okay, that's something you have to remember. Once you apply for the scholarship, you have 5 days to accept it once you get accepted. So you're gonna have to be struggling and looking at that because that's for sure.
They literally gave me $16,000, like the full freaking amount too. And like they took it away because they said you can't have it.
No, Emily. If you call them and like ask and like I had to literally I called 3 times. And
I stop the recording.
Yeah.
So they don't.
We should talk about this later because I know people are like, listen, you know, they're trying to study and stuff like that.
Okay.
Okay. All right. So the functional vital capacity is basically everything that can be expired, even like functional. I guess everything that could possibly be expired, including the respiratory volume or the residual volume, I guess. But that shouldn't be expired. And the total lung capacity is everything that your lungs can hold, can possibly hold. From the littlest to the nothing. I mean, from the biggest to the nothing. It just tells you everything that I just said. And you're basically, it's about 6 liters a minute at rest. And it should be similar to your blood output because it's like, should be similar. And it rises a lot more so than the liters of your blood during exercise because you need more air, more oxygen. Yeah. It just shows you
Sorry, can you repeat functional residual capacity?
Functional residual capacity is everything that your lungs could possibly expire past tidal volume. So it's your residual it's your residual volume and your expiratory reserve volume together.
Everything that can be expired past tidal volume. Okay. Okay.
Okay. All right. So restrictive and obstructive disorders. Restrictive disorders could be like pulmonary fibrosis, and I think pneumonia is another one. And obstructive disorders, right? Pneumonia.
Yeah.
So. And obstructive disorders is COPD, emphysema, asthma, chronic bronchitis, anything like that. And in regards to pulmonary fibrosis, does it reduce compliance or elasticity? Is it easier to breathe in or breathe out? Well, is it easier to breathe in or is it harder to breathe in?
It's harder to breathe
in.
Harder to breathe in.
Okay, and is it reduce compliance or reduce
Reduce compliance.
Yes, ma'am. Look at you. I mean, it's amazing. Okay, and their exhalation values okay, or volumes are okay, and they have a normal or elevated FEC1, which just means the amount of forced expired air in 1 second. So they basically they go like, how much air can you get out in 1 second? Okay. And then there's obviously FEC2, FEC3, and it makes sense that it would be normal because of the fact that it's hard for them to breathe in, not breathe out.
So the FVC1 would be, or just like the FVC would be normal for pulmonary fibrosis, but it would not be normal for emphysema.
Yes, 100%.
Why? Say that one again. So I know FEV1, it's how much air you have out in 1 second. The other one is in 2 seconds, and the other one is in 3 seconds. So
She
why
only cares about the 1 second, just to let you know.
she only cares about the 1 second, and that has to do with what and not with what other thing? What do you just say about FEV1?
It basically, it's normal in people with pulmonary fibrosis because they don't have problems exhaling. They have problems inhaling. So you can't really diagnose someone with pulmonary fibrosis based off of this because it really doesn't show that they have a problem.
So doesn't affect pulmonary
fibrosis. Mm-hmm.
But emphysema, yes.
People
Because
with
they have
emphysema have low percentage of exhaling because they lack elasticity.
And during pulmonary fibrosis, the problem that you have is inhaling.
Yeah.
Yes. So that means that you lack compliance.
Can someone tell me what FVC is?
It's basically forced expiratory volume, and it's the amount that you can expire in 1 second.
So I just like keep FEV and FVC like together when we're talking about that.
Yes, because they're the same thing.
The same. Okay. Yeah, that's what I was thinking. Okay.
So a problem with exhaling, is that a problem with elasticity?
Yes.
I finally got it.
Yes, you did.
It's
Yes,
an-
you did.
And chocolate.
I want chocolate. Okay.
Yeah.
All right.
Ferrero Rocher.
Okay, so FEV1, it's problem with exhaling. FBC, it's problem with inhaling. Right?
No.
No.
Okay, so
No. No.
No.
Test. It's a test in which basically can see how well a person's elasticity is, or how well your lungs can recoil and get the air out.
that's FBC.
That's both. That's a test.
Together.
That's when you go to the doctor and the doctor tells you breathe in forcefully and exhale forcefully. It's a test. They're both the same thing.
The test. Okay. I remember that.
All
So
right.
it's a test to see how well you can inhale and exhale, basically.
Yes.
Mm-hmm.
Okay. Well,
And which one was it, the one that you said that something about 1 second to inhale instead of exhale?
no, that's not a test.
Oh, so you didn't say that.
No.
I didn't mean to crack my gum that loud, sorry.
I didn't even hear you.
Okay, good.
All right. We good to go? We're good on this? I mean, I didn't really explain the second one, but we pretty much talked our way through it.
Yeah.
So, all right. So asthma is a transient obstructive disorder. Transient, which means that it's affected by certain things like allergies, exercise, different things. Is an inflammatory component. It inflames the sides of the bronchioles, and then further bronchial constriction basically makes it so that it is very small, and it is right here. So, oh wow, that's beautiful. Okay, so this is a normal bronchial tubule, and this is a inflamed bronchial tubule, and you see how the inflamed sides and the bronchial constriction basically allows that airflow can't be come through, and it's not good. Okay.
Isn't asthma that you have a lot more air in?
No, less. Well, okay. No, it doesn't really, I guess, because it's a obstructive disorder, it's,
I think you have problems exhaling more
you,
than,
you have problems exhaling,
yeah.
but it doesn't allow really airflow. It doesn't, it's not conducive to good airflow. And if you've had asthma, you can kind of, so for me, I have exercising asthma. So if it's really bad, I can't really breathe in or out really well either. Like, it's just like, I'm just totally screwed, like the whole thing. But in this obstructive disorder, I mean, but the bronchioles are closed. So you can kind of think that you can't really inhale well either. I mean, you're trying to, it's not really working though. For me at least. I mean, I don't know, but like she didn't really talk about it in regards to this. If she's talking about elasticity, she's going to be talking about emphysema or COPD. She's going to be talking about those two things. She won't necessarily say asthma, but you need to know that asthma causes an inflammatory response, which means increased mucus production and bronchial constriction and inflamed. It's inflamed. And
Yeah, she talks about elasticity. You said emphysema and what?
COPD, but she might talk about this, but it just obstructs the flow. It's a disorder which basically, I mean, it doesn't really have to do with the lungs more. It's more the bronchioles, but it does obstruct the airway. But if you're talking about less elasticity of the lungs and recoil, you're talking about COPD and emphysema. But this is an obstructive disorder, obstructive disorder too. Did I confuse everyone? I think I did, but I'm sorry.
Well, it made sense.
Yeah.
So I'm still trying to figure out about the elasticity and the recoil.
That has to do.
No, you said compliance has all to do with inhalation, right?
Yes.
Did I go wrong? Okay. Compliance has to do with inhale, and then elasticity has to do with recoil.
Yeah.
Okay. I'll probably like just have to keep on because I for some reason I had it the other way around, but it's fine.
All right, so corticosteroid for first line for all asthmatics and rescue inhaler, beta antagonists if needed. So that kind of helps open up the airway and allow for, bronchial dilation, and it basically stops the inflammation. Emphysema right here, alveoli tissue destruction, fewer but larger alveoli, and this reduces the abilities of the bronchioles to remain open during expiration. Bronchioles collapse with exhalation, which traps air and further reduces the efficiency of gas exchange. Smoking is the most prominent cause, and this promotes inflammation and destruction of the lung tissue. We have pretty much been over this, so I didn't want to spend too much time over it.
Let me ask you something right quick. That emphysema has to do also with high amounts of carbon dioxide.
Yes, ma'am.
And that increases acidity, right? Like
Yes.
acidosis.
Yes.
Okay.
So it makes your pH more acidic.
Of your blood.
But that's later on, right? We're gonna get there because I don't really understand.
We're gonna get there.
Okay.
We're on our way. We're chugging along.
Okay.
We're gonna get there. We're almost
Olivia.
at the PowerPoint.
Yeah.
Olivia, for the emphysema, what does it mean again? Fewer but larger alveoli?
Yeah. It's destruction of the tissue. The smoking causes it mostly. It basically makes it so right here, as you can see on this picture, this is normal alveoli, and this is the alveoli in people who have emphysema, and see how they're much bigger. The surface area is much smaller because of the broken down walls. It's not good.
Okay, so fewer but
problem with compliance and elasticity as well? Wouldn't it have both?
No, just elasticity, because they can breathe in pretty well. They can allow air in pretty well. They just breathe out.
The problem.
They just have problem exhaling.
problem exhaling?
Yes, because the fact that the alveoli will collapse. And this doesn't really, it traps the air, and it's not good.
Okay.
So this is when surfactant isn't working that well, and right?
I mean, you can guess. I mean, I think it just can't do that much.
Okay.
I just think that it's the type 2 cells are on the walls of the alveoli. So in fact, there's so little of them that you could probably guess that because the walls of the alveoli have been destroyed, so have the type 2 cells.
Right. Okay. Makes sense.
And so that's kind of how I don't want to speak to it as I know that, because I don't, but you can kind of infer that. If you want to ask her, I'm sure she'll be she'll explain it to you, or she'll say, no, you're totally wrong. Yeah. So
okay.
Either way.
Sounds good.
It'll make you sound really smart. Like, you know what you're talking about.
Oh yeah.
I don't know what I'm talking about. Anyways, okay, so alveoli with emphysema, they look disgusting, brown, you know, sad. And the normal alveoli, they're happy. Oh, yay. This is so much fun. Okay.
Finally, COPD shows when I've asked for it the whole time.
I told you what it was. I told you like 4 times.
Exactly. So I'm like, finally it shows after I asked 40,000 times. It actually says, like here, it says the actual name right now after I asked you 40 times.
All right. So, okay, so COPD, chronic inflammation and airway narrowing. Emphysema is a type of COPD. Accelerated decline in FEV1, which is the forced expiratory volume in 1 second. Asthma is considered obstruction, but obstruction is transient and reversible with albuterol, which is a type of asthma drug. Bottom line, asthma exhibits characteristics of obstructive disorder, but is not purely obstructive. And emphysema mechanism, inflammatory response, which basically means that the macrophages, neutrophils, and the exotonic T cells respond to tissue injury, not allergy, and they result in destruction of the lung tissue via the cytotoxic T cells, and this destroys the alveoli walls and stuff. Okay.
So an accelerated decline in FEV1 is an accelerated decline in exhaling. So you're not going to be able to exhale.
Forcefully.
Okay. And then albuterol reverses asthma, which means you take albuterol to be able to, instead of decline, just increase the FEV1.
It's just saying that asthma is considered obstructive disease. So but it's not always. It's transient. So it means it's there sometimes and then not others. So in a normally characteristic COPD or chronic obstructive pulmonary disorder, it's always it's chronic, which just means constant, chronic. It's you know, it's always there. So, but in this, it's not technically under this.
Because asthma doesn't have to be chronic. You can have chronic asthma, but some people don't have chronic asthma. That's why it's not.
Exactly.
Yeah, that's why it's not. Yeah, that's why it's transient.
Yes. Okay.
Did you go over the emphysema mechanism?
Yeah, just showing you that there's an inflammatory response and these certain basically your immune system starts attacking your lungs, and this is what causes the alveoli destruction, because it's responding to the tissue injury. It's just really well, no, sorry, I messed up. Okay, so basically your lungs, your immune system will respond to the tissue injury that's caused by smoking or certain things, and it will cause inflammation and further damage of your lungs.
And then the macrophages, neutrophils, and cytotoxic T cells, which are part of the immune system, will go to fight that infection?
No, they will go and inflame it. They'll basically so
we need to know that.
No. I don't think we need to know that, but you're right. So there's an inflammatory response. It inflames the lungs. The macrophages, the neutrophils, and the T cells will come and respond to the tissue injury and not allergy. And this results in more destruction of the lung tissue.
Okay.
Because they're responding to the inflammation, and it's just bad. You don't like that.
Yeah, I remember she said she's not gonna ask us about that.
Okay.
So she's not gonna ask us about like the macrophages and the neutrophils and the cytotoxic.
I mean, she said that on the lecture.
Okay, perfect.
All right, so this shows you these are all part of COPD, emphysema, chronic bronchitis, and asthma. But asthma is not purely. It's not like emphysema. It's transient. It's not always. All right.
Olivia.
Yeah.
I want to hear my voice. In the slide that we just passed, emphysema would be a problem exhaling or inhaling.
Exhaling.
Okay, so exhaling, so it will be, I keep on forgetting. So it's
Elasticity.
Elasticity.
problem exhaling, that would be elasticity.
Yeah.
Just think of like EE, elasticity.
Thank you, Morgan.
exhaling.
And I needed that in my life. I would have never.
Wait, say that again, Morgan.
Like the two E's go together. So like,
Elasticity, exhaling.
yeah. So if you have a problem exhaling, you have a problem with your elasticity.
Oh, okay.
Yeah.
And if you have a problem with compliance, you have a problem inhaling.
Uh-huh.
But it doesn't
Save my
matter.
life. You just saved my life.
Exactly.
That makes so much sense.
So if you
Yeah.
problem exhaling, you have a problem with elasticity. What about asthma? It's the same thing. Exhaling elasticity, chronic bronchitis, the same thing.
It's really not. Just don't compare it to that. Just don't even think about that. It's different. It's like, I mean, I bet you explain it, but it's basically inflammation of the bronchioles. And if you could imagine, if there's excessive mucus production and inflammation of the bronchioles, there's no air getting in or out. It's very little.
That's exactly what asthma is, what you just said. It's an inflammation in the bronchioles, not in the lungs, and it has mucus. So obviously the air flow is very
Limited.
It's affected.
Yeah. That's
because air
exactly what
can't
asthma
get in
is.
or out properly.
And you don't always have asthma because you don't always cannot breathe. So that's why it's transient. But you always have emphysema. So that's why it's not considered.
Repeating that inflammation of the bronchioles, not in the lungs. So
It's transient. So it means like certain things will like act like make your asthma act up, but it's not always acting up, if I'm correct. So like someone's allergic to cats when you're around, that's when your asthma is going to act up, but you're not like always having like an asthma attack or something like that. That's how I'm understanding it. That's what it means by transient. It's not always a problem, but when it is a problem, then your the bronchioles constrict and your airflow is affected.
And then they give you a beta agonist and you're good because your bronchioles dilate.
Right.
And no matter how inflamed your bronchioles are, if the bronchioles dilate, there's opening there and you're good to go.
So that's what the inhaler is a beta
It's different.
Agonist.
okay.
oh wait, agonist.
Sometimes
Mm-hmm.
they can give you an inhaler and it can also be corticosteroids.
Oh, okay.
Like
Beta agonist causes vasodilation.
Bronchodilation.
It'll cause your bronchial tree to open up. It's
So
like
you
an
get the
antihistamine.
air in and out of the lungs better.
Yeah, it's kind of like an antihistamine that's going to open up your bronchial tree.
yes, ma'am. All right, let's go on to the next one. We still got another PowerPoint.
Yes.
You have
And it's
another
very
PowerPoint?
hard. The last one is very hard.
Yeah,
Mhm.
it's difficult with the PaO2, PO2.
I got you guys. All right. So this is just showing you that in people with emphysema and COPD, they have a barrel chest, which just means that they have more air inside their chest because they cannot get it out. Got me?
That's interesting. So so they have more air inside, but they have trouble getting it out, exhaling.
Yes.
Yeah.
Okay.
Because they can breathe in, but they just can't breathe out as well.
That's so weird how it does that to your chest.
Well,
I guess just because you have so much air built up.
yeah.
Wow. That's crazy. Body's weird.
All right, so this is just saying what we've talked about again. Pulmonary fibrosis, functional lung tissue is replaced with fibrous connective tissue, can result in inhalation of small particles that escape the filtering mechanism that we have in place, like the, because it's under 6 millimicrons or whatever the hell, how you say it. And this includes asbestos, coal mine, like the coal, and this can also be called black lung. And it's a restrictive disorder, which means that it cannot, compliance is reduced and low, which means they cannot breathe in. And the lungs cannot expand or function well in gas exchange because it's replaced with fibrous connective tissue. It's the same thing in regards to like the lungs, not the lungs. Why am I'm talking about the lungs, the liver. When you have fibrous connective tissue that replace the healthy liver tissue, this inhibits the function of the liver. Same thing here. It inhibits the function of the lungs. It says recoil enhanced, which just means elasticity, and it can be either normal or enhanced, but compliance is reduced, which means they can't breathe in.
So why does it say recoil enhanced? Isn't that meaning that elasticity is working perfectly fine, but then
Yes.
its lungs cannot expand?
It just means that it's like the rubber band sheet, like, you know, like the really heavy rubber band. You know how it's really hard to stretch, but when you let go, it bounces back really quickly?
So elasticity works, but it's harder. It's putting more pressure.
No. Compliance is reduced.
Okay.
Recoil or elasticity could be either enhanced or normal.
And enhanced means?
Better. Like the person cannot inhale because they cannot expand their lungs, but they can exhale very well.
Okay. Okay.
All right. So guys, let's break it down here. So atmospheric pressure is 760 millimeters of mercury, and this is the number that we're going to be talking about. Now, partial pressure is the amount of basically a part of that atmospheric pressure. So if we're talking about oxygen, the percentage or the partial pressure of oxygen in regards to the number 760 would be 159 millimeters of mercury. And how you get that number is based off the percentage of oxygen in 760, so, or in the atmosphere. And when you're talking about gases in the atmosphere, there's two main gases that we're going to talk about. There's nitrogen, well, there's four, whatever. Okay, there's oxygen, there's nitrogen, there is
Carbon dioxide.
carbon dioxide, and there is water, or
What?
HO2, H2O, when you can't get the water formula. Gosh. Okay. And nitrogen is the most. Okay, so nitrogen has 78% of the total of that number, or total, basically. And I thought it was like 100% oxygen. I was totally wrong. And if it was, we would all implode if we ever light a cigarette. Okay, so that is why, probably. And so this makes up a majority of the atmosphere in like what's in the atmosphere. Okay. So when we talk about partial pressure later on, we're talking about the amount of a gas in that area. Okay.
Yes.
Okay.
You're very good, Olivia. You're doing great.
Thank you. All right. So inspired air, we have in the normal regular atmospheric air, you have 78% about or 597 milligrams of mercury. And that really doesn't mean much to us because why do we care, right? Why do we care? Well, it translates exactly into the alveolar air. Okay, so if you can think that if we have nitrogen in the air around us, we're going to have nitrogen when we breathe in. But do we really need nitrogen? No, but I guess there's nitrogen. Okay, I'm not going to go in that. I'm going to literally, I'm just not going to talk about nitrogen because we're just not even going to get into it. But there is nitrogen. It does come into our bodies. Okay, just so you know.
That's it.
Okay. Oxygen. Okay, oxygen is breathed in too, but it's only about 21% of the atmospheric air. And that correlates to about 159 milligrams per mercury out of the total 760 milligrams of mercury is the atmospheric pressure. Okay, so that's how much you breathe. Well, that's how much is in the air. And when you breathe it in, okay, when you breathe it in, not when it gets to the lungs, we're going to talk about that, and that's right here. You also breathe in water because there's water in the air. You know how they talk about the humidity is 100%, the humidity is 50%. Okay, that's the amount of water or moisture in the air. When you breathe in, like if you are on a really hot day and it's really humid, there's a lot of water in the air. There's a lot of humidity, which means water molecules like in the air. Now you're going to breathe in some of that, and it's about 0.5%. But you can imagine that when you get to the alveoli, that there's going to be more water. If you just think about it, because you remember how we needed a thin layer of water on the alveoli. So that's going to come into play later on. That's about 3.7 milligrams per mercury in the inspired air. So that's when you first breathe it in, but not when it gets to the lungs yet, just like when it goes in your mouth, okay? Or whatever, your nose. All right, then you have CO2. And there's a very small percentage there too. There's about 0.04%. But can you imagine that your body exhales CO2? So, or that's what it needs to get out. So you can imagine that in the body, there's going to be more CO2 in the alveoli once we've all said and done. Okay, so that's going to be a higher percentage. Now, so this totals up to 760. So you need that total. If you don't have that total, then you don't have everything that you're breathing in. Okay, so alveolar air, okay, when you're talking about alveolar air, you're talking about the air that is located in your alveoli when after basically gas exchanges occurred, okay? So as you look here, so you breathed in a little bit of nitrogen and a little bit went into your bloodstream, which we're not going to talk about. But as you can see here, this number right here, 569, is lower than this number, okay? So that's how you know that some of that came into your blood, okay? Which isn't a bad thing, all right? Not bad. Now, you have oxygen, okay? And you can imagine, based off of that, you need oxygen to your tissues, that you're going to want to intake that oxygen. So as you can see here, 159 millimeters of mercury, it's going to be less than in the alveolar air after it has been absorbed into the bloodstream, right? After diffusion has happened. So as you can see, this is higher than this because the oxygen has come into the bloodstream. Now, right here, as you can see, now the amount of water or HO2 is higher in the alveoli because of the fact that you have that thin layer of water, right, to help with the lubrication and help with the diffusion of gases or gas exchange. So it's going to be a little bit higher, which is okay, right? So it's about 47 compared to 3.7. Okay. Now we get down.
Don't we also, when we inhale, don't we like humidify the air and warm it?
Perfect. Yes, exactly. And we also, when we breathe in, we humidify the air, so we make the air even higher.
More water.
Yeah. Yes. All right. So in CO2, okay, right here, as you can see that this number went way up, okay? And because you can kind of think that it went way up because of the fact that your body took the carbon dioxide and moved it from a high gradient in your blood to a low gradient outside into your alveoli. And it did the same thing with oxygen. It took the high amount in your alveoli and put it into your blood. Okay, so that is why there is more carbon dioxide in your alveoli after gas exchange than before gas exchange.
I am sorry, I didn't get that.
Okay, so you can see that there is much higher, right? Milligrams per mercury. There's about 40 compared to 0.3 before gas exchange occurred, before you breathed in the air. Okay, there's more carbon dioxide located in your alveoli after gas exchange has occurred. And the reason that is because your blood is diffusing from a high to low gradient. So it's taking the carbon dioxide in your blood and putting it in the alveoli to be expired.
The carbon dioxide, bringing it from the tissues to the alveoli?
The blood. From the blood to the alveoli.
Okay.
Okay.
So gas exchange is gonna be like taking like the hydrogen and the nitrogen and the oxygen and the CO2, like taking all of that from the blood and then putting it into the alveoli for expiration.
Depends
like
on
that's
what you're talking about. So okay, so let's do this. Right, I want everyone to write down blood. No, let's write down capillaries and let's write down alveoli. When you're done.
We're done.
Okay, now I want you to, from the capillaries, from that column, I want you all to write down those 4 gases. Well, really, it's only gonna, well, not 4. I want you to really write down CO2 and oxygen really much. That's really the ones that I want you to write down. The other 2 don't really matter, and I don't think she's going to ask you about them unless she asks you about like why is the water higher in the alveoli than in the atmospheric pressure. But she's mostly going to ask you about oxygen and carbon dioxide. So once you're done with that, we're good to go. Then write the same 2 down on the alveoli, under the alveoli.
Done.
Okay.
All right, now I want you to write an arrow from the, so if we're talking about oxygen, I want you to do an arrow from the alveoli pointed to the blood or the capillaries.
So an arrow from alveoli to capillaries.
Olivia, can you draw it?
Yeah.
I wish I had an iPad so badly. This should just make my life easier.
Oh, for sure.
Tell me about it.
100% make your life so much easier.
I'm like trying to get an iPad out of my boyfriend so badly. He's like, you don't need it. I'm like, but everyone has one.
I don't.
My boyfriend was like,
need it. Tell him you need it. Don't say everybody
need
has
it.
it. Just tell him you need it. And definitely, if you still don't need it, it's Christmas and he has to get you whatever you want.
My boyfriend was like, I would buy you the iPad, like the new iPad Pro, if I had $800 to spend.
I just want the Air. I don't mind having that one.
Yeah, that one's like 300, right?
Morgan, when we're studying, my whole study group is using their iPads, and I'm here on my little paper just writing everything.
No,
I
literally.
Mandy, don't
so
say
much
that,
shit for her
Mandy.
paper.
Mandy, don't say that because the group that you study with, it's hearing you right now.
I always tell her, I'm like, Mendy, after every time we go through a PowerPoint, she goes, hold on, I gotta get my papers together. And I'm just like,
That's literally me with my big ass notebook and my pages of notes.
And then she encouraged this whole paper thing by buying binders, and I'm just like, she's never gonna switch. It's never gonna happen. She's gonna stick with
Whatever. I have paper.
I just told her it's so much easier because we'll be studying and she's like, hold on. I've lost a page. Hold on, wait. I'm just I'm like
Thing about it, Morgan, the good thing about it, like once you're taking notes and sometimes you miss something, you can record it in the meantime, the professor, and then you could just go back and review the recording while you're taking notes.
Yeah.
Oh, that's nice.
So like what you
touch the letter, whatever you're writing, and once you touch it, it tells you in the background what she was saying while you were writing it.
What?
Are you
yeah,
kidding me?
that's
Yeah.
so an ability.
I'm sold.
I'm telling
iPad.
so you'll record her. You record her like while like you have your iPad recording and you're listening to the lecture, right? And you're writing as she is talking. And then you finish your notes and you click on the letter or on the word. And when you click on the word, it starts playing the recording of what she was saying while you were writing.
That moment. Yeah.
So that you can listen to her while you see what you're writing. And it shows you writing it. Like it's like a screenplay of like you writing while she's talking.
Yeah.
I have notability as well.
That's
Yeah.
notability. That's notability.
I
Yeah.
like that one, yeah.
Okay, if anybody,
And
I know you're in Fort Myers, but if anybody in Fort Lauderdale has that and wants to show that to
You
me,
say it from Florida, right?
Yeah, I have it.
Get it on an iPad.
And I have the $300 one. I got like the, I don't know if
I
this
have
is
that
like
one
the 6th
too.
edition.
I have this one too. I have the same one.
Yeah, because the Pro is like too much money for nothing. Like you're just gonna write notes.
That's like almost as much
I
as a
honestly don't know anything about these. I just got this as a gift, so I have no idea which one I have. But I honestly don't have any idea. My boyfriend gave it to me.
The iPad is so good.
My boyfriend bought this one for me too.
Yeah.
Aww.
Morgan, your boyfriend needs to step up. I'm gonna show this recording. Show it to him.
Morgan, it's $300. He could definitely get it for you for Christmas.
Yeah, you
I
deserve.
know.
Okay, back to this. I'm ready for
Yes.
you.
guys, I have a question.
Uh-huh.
What's it called? Cellular diffusion? No. Like, what is it called?
Wait, what are you asking?
My brain stopped working.
Diffusion?
No, it's something specific. Like
You lost me.
Related to
Hey,
what?
gas exchange. Thank you.
Oh.
I was like not even helping her. She like came up with it on her own. We're like, what are you talking
She's
about?
like in her mind, like having the conversation with her other like brain. She's like communicating.
Like when you can't sell exchange, but you can do everything else. Change. All right, guys, there you go. Here's my little chart.
Okay.
You did it a different way.
So capillaries.
Capillaries, the CO2 will move from the capillaries into the alveoli because it goes from high to low. And in the alveolar air, well, it's not after, well, it's basically during gas exchange. During. And oxygen moves from the alveoli to the capillaries.
And so gas exchange is going to happen during inspiration, correct? Correct? Like when you are taking in the air, when you're inhaling? Okay.
Okay, let's continue.
Okay, so in regards to high altitude, while the atmospheric pressure is less, the amount, basically the percentage of air of the certain gases is still the same. So the oxygen is still the same amount of percent, but it's just lower because the overall atmospheric pressure is less. Got it? So
Okay.
Okay.
So for example,
atmospheric pressure is less or more, the amount that you're gonna get, it's always gonna be the same, right? It will still be the 760 mmHg.
Well, no. So atmospheric pressure, if you're at sea level, it's 760. If you're at 2,000 feet above sea level, then it's 707. But it's directly correlated with because it's like the same. It's just like a ratio. I mean, do you know what I'm saying? Like it's like the same percentage of the lesser amount.
Okay. So sea level 760, and then what about the other one?
It would be 159, the partial pressure of oxygen in the air.
So you actually get a little bit less of oxygen into your system.
Yes.
Yeah, so you get less oxygen at higher altitude.
That's why she said when she went to like the mountains, she couldn't breathe as well as when she was here in Florida.
Yeah, and that's why it stimulates the production of red blood cells so that because your body doesn't realize that you're at a different altitude. It just thinks that it's not transporting oxygen as well. It doesn't understand. So
that's when it's related with hypoxia and erythropoietin, all of that.
Mm-hmm.
Okay.
All right, so it's just showing you the same thing as before and the correlated partial pressures of each thing. So depending on what you're talking about. So in inspired air, variable, that's what I was talking about, humidity in the air, and it's different depending on what's going on. And the alveolar air is directly proportional to the inspired air. So if you have less partial pressure in the air, then you're going to have less in the alveolar air. Got me?
I'm sorry, can you give me the definition of partial oxygen pressure? Like what is that?
Well, it depends what you're talking about. Depends if you're talking about in the blood or you're talking about in the air.
In like let's say in the air.
Okay, so then it would be the amount of oxygen, and it's directly proportional to the amount of atmospheric pressure. It's kind of hard to explain. So it's basically the amount of oxygen in the atmospheric air, but it's measuring pressure. So it's the partial pressure of oxygen related to the air, the atmospheric pressure in the air.
Okay.
Does that make any sense? That doesn't sound like it made any sense. Does anyone have any better explanation? Or
I think I'm gonna use Google.
Thanks. Google's great. Yeah, I totally agree. Oh gosh.
This is like a little complicated.
All right, so this is just showing you that the partial pressures of the gas in the blood is kind of it depends. So, but it's directly proportional to the partial pressure of gas in the air. So like I was talking before, if there is less amount in the air, then there's going to be less amount in the alveoli.
Yes.
Which makes sense.
Mm-hmm.
And temperature doesn't normally vary it. And really just the most important thing that you have to know about the slide is that if there's a higher partial pressure, then there's going to be a higher concentration in the alveoli. And if there's a higher partial pressure in the alveoli, there's going to be a higher one in the blood. Okay. And that's shown, well, I can't go backwards. Are you kidding me? Right here. Okay, if you look right here, it's 760. This is 157. 157. 159. This is 105. This is 100. It should be within 5 between. This is 707. This is 148. This is 97. This is 92. So as you can see, this means partial pressure right here. P means partial pressure. So as you can see, the lower the atmospheric pressure, the lower the partial pressure of oxygen. This it's a lower partial pressure in the alveoli of oxygen, which makes it lower the partial pressure in the arterial blood. Does everyone understand that?
Yes.
All right. This shows you how it diffuses from high to low. This shows you the same thing as we looked before. If there's a thicker walls, there's going to be less diffusion. Okay. So we're going to do the same thing that she did. If you don't have these definitions, then we're going to write them down again. PO2 is the partial pressure of oxygen in the in like the whole, it's not specific, it's just the partial pressure in the blood, but it's not specific to arterial blood or the venous blood. And PaO2 is the partial pressure of oxygen in the arterial blood. All right, you got that? Now I want you to write down one more. PCO2. This is the partial pressure of carbon dioxide in the blood, not specific to the arterial blood, just the blood.
What was it? PCO2?
Yes, ma'am. Because she talked about it, but she never explained what it was. And I just sat there and I was like, I wonder if anyone knows. I just think everyone just caught on. They're like, okay, must be carbon dioxide.
Partial pressure of carbon dioxide in the blood?
Yes, ma'am.
Okay.
So we're good on that. All right. So basically we measure PaO2 very closely. We want to see it because this directly corresponds with how well the alveoli are functioning in their job. If they're not functioning in their job, then the gas exchange will be, this is how you can tell, because of the fact that PaO2 is directly corresponds. So it should be 5 less than the partial pressure in the alveoli. So do you remember that chart I drew? Remember how I said the alveoli to the capillaries? So if the partial pressure in the alveoli of oxygen was 105, what would be the partial pressure of oxygen in the arteries?
100.
100. Perfect. Perfect.
And if it's not, then there is a problem with diffusion.
Or yeah, gas exchange. Same
Yeah.
thing, right? Okay.
And what could be like, what is my diagnosis?
Emphysema.
Emphysema.
You're so smart.
I know.
Look at us. We're gonna be nurses.
I'm halfway there, guys. Just kidding. Okay. All right.
Like, what do you have? I don't know, emphysema. That's all I know.
I don't know calcium. It's calcium. All right. There we go. So that's it. There we go. We completed it. Just kidding. We're done. So this is what I was talking about. It's exactly what I was talking about. Oh wow, this beautiful line. And they should only differ by 5 millimeters per mercury of whatever the hell. Okay. PO2 is at PO2 of 100 milligrams per mercury. The hemoglobin is 97% saturated. And why is it 97% saturated? Why isn't it 100? Tell me.
I didn't understand the saturation part, so I can't tell you.
Okay, so I think that has to do
Oh, wait.
with that there are some hemoglobins that cannot bind oxygen.
Yes, ma'am. Yes. Okay. So it's because some hemoglobin cannot bind oxygen, and these are called met hemoglobin. And it's because they're oxidized, which just means that they have a +1 charge on top of their +2 charge. And because of that, because they need a +2 charge to bind oxygen, because oxygen is a -2 charge, if it does not have a +2 charge, then it cannot bind oxygen. Okay, so it just travels around. And it's just like, kind of like, what's up, dudes? I can't do anything. So it just sits there and kind of chills. And hemoglobin, about 20 milligrams out of 100 milligrams of blood is, oxidized, whatever the hell. I don't know. I honestly don't know. I remember seeing it later on, but I can't remember.
Olivia, I have a question that you might know the answer to.
Yes, ma'am.
The little thingy that they put on the finger,
Yes.
does that measure the PaO2 or the PO2?
It measures
Saturated hemoglobin.
amount of oxygen bound to hemoglobin.
So it's the PO2.
Yes. No. Well, no. Because PO2 isn't. Well, that's the partial pressure of. Oh, I guess. I mean, it's just. It's all
CO2 is the
oxygen.
partial pressure of oxygen.
Yeah. So it's the amount of oxygen in the blood. So it's not
Because I thought it was in the arteries. Like I thought that thingy measured it in the arteries.
No, I'm guessing it's just in the no, it's basically measuring the amount, how well the hemoglobin, how much oxygen is on the hemoglobin. It's
Okay.
like how well is your hemoglobin carrying your oxygen. We'll get to it though, and it'll probably have the answer on the slide. I mean, I can look. Tomorrow.
So if I have emphysema and I put that thing on my finger, it's gonna read 97 or 98. Because
No.
it's emphysema, because the emphysema is especially directed to the diffusion. The PA2, the PaO2.
No, you won't have good. No, it won't be good. It won't be good. It will be about, I mean, depending, it'll probably be around 70, 75. Because there's not, the oxygen is, the amount of oxygen that you intake because your alveoli aren't working properly is less than. And the only thing that can control it is impaired. So the chemoreceptors are impaired because you have higher amounts of carbon dioxide and lower amounts of oxygen. So the amount of oxygen that your hemoglobin are carrying is also impaired. Like it doesn't have enough.
Last class, we get to cover the whole thing or no? Or we stopped somewhere? Did we get to cover this whole PowerPoint or no?
I don't remember forgetting to this part.
Yes, we did go over this in class.
So right here, so it shows you the percent of hemoglobin saturation. So how much oxygen is loaded on the hemoglobin?
But right there it says normal arterial blood. So that one is specifically to the arterial one. I don't know, like that confused me.
Okay, but is the actual thing, she explained it, and it's basically a light that shines on it, and the hemoglobin, when oxygen is bind to it, shine a certain type of color so that it can sense that color, and there's a bunch of data things, and it basically calculates it
and
that
also
way.
like it confused me the most because okay, so my mother-in-law, she's a doctor, and then I went the other day to his her dad's house, and he has emphysema and diabetes and a bunch of things. So he put on that thing on his finger, and it was around like 94 or 95, and he has emphysema. And he told me that the doctor told him that if he gets 92 or below, that he had to call the provider and go to the hospital. 92 or below.
Wow.
And then I asked my mother-in-law, and she said that if someone has it in 80, they're like she basically said that they're like almost dead, like they need to go to emergency. So that's what
he wasn't receiving oxygen like through his nose.
No, they don't. Not everybody. My people, the person I live with, no, she doesn't.
No, I'm talking about Zadie's, like your grandfather. Not
no, he doesn't. I mean, at night
through his nose.
At that time, no.
And his
He has emphysema. Like that's one of his conditions.
and his SpO2 was 94.
Yeah.
That's not bad. It's really not.
That's
No,
really not bad.
it's okay. Like that's normal. But then they said that if you have it at 80 or
That's
Oh no,
that,
you're like you're dead. You're dead.
No, you're
yeah,
not actually. So it's really funny. The person I live with, she's been down to like the 70s, and she felt really bad. But she's like, she doesn't have insurance. She like has Medicare, and it's not really comprehensive. She doesn't like to go to the doctor that much. And when she does, the doctor sucks because all that stuff, and they're overworked and stuff. But so she doesn't like to go to doctor a lot, and she was okay. Like it was really bad. I mean, she was hurting, and she was tired, and she wasn't getting good oxygen diffusion and all that stuff, but she was living, and she was okay.
with 70,
Yeah.
that's like the part that I didn't understand. Like that's the part that's confusing me because that's
I
not
guess
what they're saying. And like I also looked it up in Google to make sure, and it said that if you have your oxygen lower than 92, like that little machine says lower than 92, then you should call your provider. So how can someone with 80 like be, I don't know.
it's when they don't, I think I don't think you're not, it sucks. I'm guessing it feels bad, and you probably aren't getting good enough oxygen, and they want you to have high enough oxygen and all that stuff. But if they don't want to go to the hospital, you can't force them to.
Oh,
I
yeah.
mean,
And then the other thing that confused me is that the professor said that PO2 is not the same as PaO2 because I already know the differences. So someone with emphysema, they have trouble in PaO2, right? In diffusion, but maybe it's not affecting the PO2. Maybe it's only affecting.
it is.
It is? Okay.
Because
Okay.
in regards to the chemoreceptors, right? They don't, in the peripheral chemoreceptors in the carotid sinus and on the aortic arch, that's what senses the PO2 in the blood. And in people with emphysema, when they constantly have high CO2 levels, the oxygen, when it gets below 60%, that's when it kicks in on hypoxic drive, and it starts breathing really heavy and starts that. And basically it's just a constant cycle.
Okay.
And that's 60, is that crazy? I don't, it's below 60 milligrams per mercury or whatnot. Okay, well, now that we had that fun conversation, we have to go all the way back here. I know, you guys are so excited. Are you still there? Are you alive?
Yeah, we're here, but we're here.
I'm about to go grab a snack.
This content is very like difficult or
Delivery.
Oh my god.
Hey, delivery.
What about a 5-minute break or 3-minute break?
We can do that.
Like a 3-minute break.
Okay.
Olivia is feeling now how the professor feels when we ask for a break. She's like,
Oh.
1.5, and I'm counting.
She loves breaks. She loves them. Don't even lie to yourself. She loves them. It's a
I feel like she can breathe well with the mask, so that's why she asks for breaks.
That's really messed up. Like, I understand the situation and everything, but I think she should just take the class from home better because it's so uncomfortable for her. I think eventually it could like affect her health. Like she's not
No,
being
she's
able
fine.
to breathe.
She's
normal.
fine. She's fine. She hates the mask. She hates wearing the mask that has the plastic on it. She doesn't mind.
Are you on class?
What?
Are you on campus with her?
Yeah.
Oh,
That's crazy.
must
Now
be
I don't
nice.
have it in my class.
I know.
Have you switch 1 week or something? Just
Okay, well, no one goes, so I just go every class.
send her tomorrow, please. We need her for Myers. One day, you've had her the whole semester.
Oh my word. She'd probably
I
go
love
if someone
her.
asked her. She'd
Oh,
probably
you guys
go-
know we have class on Monday or Tuesday, right?
What time? Anyone know?
She said, what'd she say, 10 or 11 on Tuesday morning?
All right. That's not-
Morgan, I'm jealous right now
Why?
because you have a kitchen. I've been okay. Mandy knows about it. I've been 2 months without kitchen
What?
because they finally approved me the permit to finish my kitchen.
Oh my god.
For 2 months. So I'm
Shouldn't be eating right now, but whatever.
delivered.
All right. Are we taking a break or are we like?
No, you can continue if you want. I'm just getting a snack.
Emily walked away for like a 2-minute break. We're just here.
Wait, I have a question. What material are we going over tomorrow in class?
Respiratory and endocrine.
No endocrines on. Oh wait, never mind.
Let me before Emily comes back. Let me go dress.
She was saying she was gonna do it on Tuesday, so maybe she's gonna finish it up on Tuesday. So
Maybe. I don't know. I thought she was gonna do kidneys. I love kidneys. I don't know why she doesn't do kidneys. I like kidneys.
Olivia is tired.
Kidneys are important. You know, we were supposed to do a Kahoot tonight, but
We're supposed to.
Yeah.
it's 11 o'clock now.
I
So
think let's try to finish this and then maybe Kahoot another time.
yeah,
I wanted to do the Kahoot.
me too. But I guess if
But
what are we gonna be up until 12 in the morning? Not 12 in the morning. We're already gonna be up till 12. Do you want to go?
We need to talk. We need to talk less and listen more to Olivia and move on.
agreed.
Okay.
yeah, it's been 3 minutes. Let's go.
All right, let's go. I could have peed. Okay.
We're still recording. No one's gonna get this far in.
All right. Well, I die of embarrassment. There's so many things that this could like somebody could like video do this and nobody cares that much. I don't even. Anyways, okay. All right. So breathing oxygen increases dissolved oxygen in plasma only. Okay. And yeah, that's at normal PO2 about 0.3 milliliters per 10 milliliters. It basically means like the things that are not on hemoglobin, like the oxygen molecules that are not on hemoglobin. Okay. Does not change that bound to RBCs or hemoglobin. If PO2 doubles, oxygen dissolved in plasma doubles. Okay, makes sense. She didn't really talk about this, so I don't even want to talk about that. Anyways, okay. For blood to be delivered, it must come off the hemoglobin, becomes dissolved in the plasma, and then immediately equilibrates in the tissues. Increasement of plasma PO2 increases diffusion rate. Okay. Breathing oxygen enhances tissue delivery greatly, but changes total arterial. Okay, don't even know that. I just want you to know. Just want you to focus on that hemoglobin will drop off oxygen to places in which oxygen is not there, or is it less than. So if the partial pressure of oxygen is less or is lower, then the hemoglobin will be like, hey buddy, I'm gonna give you free oxygen. Here you go. You're my friend. Okay. So just like drop it off there and be like, hey, I know you needed this. Here you go. Right. But it's like directly correlated. So as you can see, I hope the chart's next. Okay, perfect. All right, so I can't put this anywhere, but so if we come up here, okay, when we're talking about 100, so we draw our line all the way up, right? Okay, so 100 is not very likely, but in the alveoli, there is 105 milliliters per mercury, basically saturates all the hemoglobin. So when it goes into the hemoglobin, right, the partial pressure in the alveoli is about 100% or whatever, however you want to say it. There's a lot of oxygen there. It doesn't need any oxygen, right? So it loads all of it onto the onto the hemoglobin, and so the hemoglobin will travel all the way, and as it goes across, it will dump some places, but very little, right? And when the partial pressure in a resting cell is about 40, so when it gets to the tissues, the partial pressure is going to be about 40 milliliters of mercury of oxygen. So the partial pressure in the tissues is about 40 milliliters of mercury. Now the hemoglobin know that it needs oxygen, so it's going to dump more. So basically it's right here, the hemoglobin's only has about 75% of its oxygen left. So if there's 1 billion cells, there's only like 750 million cells of molecules of oxygen left. Okay, so if we talk about percentages, okay? If I confuse you, I'm sorry. But there's about 75% of oxygen left on the hemoglobin because it dumps a lot of it to give it to the tissues because they're not oxygenated because it's its friend and it wants to give its oxygen if it doesn't have any. Okay? And as the partial pressure in the tissues goes down, the more oxygen that the hemoglobin will dump. You got me?
I got a little lost, not gonna lie, but
Me too.
I feel
That
like as
one I
I
didn't
just like,
understand much.
Okay, so let's explain it one more time. So hemoglobin is perfect, like she explained before, and it is pretty perfect, okay? It can only be oxygenated about 95% because some of them can't load oxygen, okay? But for most of them, it does. And when it does, it will travel around the body and it will unload some oxygen to places where it needs it. But when it gets to the tissues, it has most of its oxygen, like from here, right? And as it gets to the tissues, it's the partial pressure in the tissues of oxygen is about 40 milligrams per mercury. And is that good? No. PO2 of 40 is not good. We need more oxygen. So the hemoglobin will be like, here, friend, here's more oxygen. We need to give you some. And so it will unload a lot. So about 25% worth of its oxygen so that to give it to those resting cells so that they have oxygen.
Oh, wait, so the graph is going from there to here. Like, you know how graphs like usually go like that?
Yes.
That one is doing reverse
Yes.
because it's fully of the hemoglobin is full of oxygen.
Yeah.
And then while if it delivers its oxygen to the deoxygenated tissues, then it decreases.
Yes.
Got it. Okay.
Exactly.
Did you understand, Morgan? So
Not
how you know how the curve goes from here and then it goes down?
yeah,
Okay, so the hemoglobin, the blood is full with oxygen, right?
right.
And then you know how the blood needs to go to the tissues to give
Yes.
the tissues and the organs oxygen.
Mm-hmm.
So while it's giving oxygen to the tissues, the oxygen in the hemoglobin is decreasing because it's giving its oxygen to the tissues. So that's why it's going down because it's losing oxygen.
Okay, makes sense. But it says, so I'm just trying to think of like this other graph. So there's a bunch of oxygen in the alveoli, and that's what it's showing here where it says alveoli 100, and then it's getting released into the, you know what picture I'm talking about? It shows the alveoli with the oxygen and then like an artery or something with hemoglobin and and the oxygen binds to it. I'm trying
Yes,
to
you're
relate that
talking
to
about the
graph.
PO2 and the PaO2. I know which one she's talking about.
So it's just talking about the partial pressure in the alveoli. And because the partial pressure is very high and 100%, the hemoglobin won't dump any of the alveoli off. Like it won't dump any of the oxygen off. So we'll keep it on there. And when it gets to the tissues that are deoxygenated, then it will dump its oxygen on them, but not all of it because it needs to reserve some for if you run out of oxygen, if you stop breathing.
Okay, makes sense.
Okay, yeah.
And you can assume if somebody has emphysema that they're not going to have 100%. They're not going to, the gas exchange is going to be impaired. So it's going to be like here, like right there, and maybe even lower, depending on whatever you're talking about. It's going to be lower in some, higher in others, but it's going to be impaired to an extent.
That's what I don't understand a lot because, but I mean, we can continue either way. Because like I understand that someone with pulmonary fibrosis, they won't have a lot of oxygen, but someone that has emphysema, they can breathe oxygen. So that's like why I don't understand that a
Okay,
lot.
because, yeah, so pulmonary fibrosis, their entire lung, their functional lung tissue is impaired. They're not going to be able to, it's not going to be as good either way because they can't breathe in, but their alveoli are still working, I think, a little bit. Okay. But in people who you should probably ask her that specific thing about the fibrosis because I'm pretty sure that it would impair the alveoli too. I don't think it would like spare it. But in cases of emphysema, your lung, your alveoli, which assist in gas exchange, doesn't have the amount of surface area that it did before because of the walls that are breaking down. So it doesn't diffuse as
Diffuse.
good.
Yeah, I understand that now. Okay, that's right.
Sorry. Oh
Okay.
my gosh, flip that. Okay.
Got it.
Oh. Oh.
No, don't stress about it.
Jocelyn, you're eating bread at this time?
Life is beautiful.
I'm gonna make myself a sandwich later on.
You don't need to know this. Don't even look at this picture. It's really
Oh.
ugly.
I don't see anything.
If you can eat bread, I can eat bread too at this time.
My God,
Nothing
my
pretzels.
family would kill me if
Patience
they
of
found out I'm eating bread at this time.
Don't let the mind limit yourself, my friend. Go.
My boyfriend would be like, "Okay, Emily, just know you're gonna feel like shit in the morning," and I'm just like, "I don't need to hear this from you. I don't need to hear somebody
Wow,
eat."
really? Wow.
No, like, cause I have like stomach problems, so I can't eat late. So
Oh.
he's kind of like my buffer, and he's always like, "Okay, like, you know, you're gonna feel bad, like, don't do it."
Bad thing about it, Emily, is that you are my friend, and whenever someone's around me, they eat.
All right.
It's
So
very true.
this is just talking about in the pulmonary artery, you're going to have lesser oxygen and more PCO2, which is the carbon dioxide. The partial pressure of oxygen is going to be less relatively, and the partial pressure of carbon dioxide is going to be kind of more. Kind of.
This is the only thing I've understood for the past 30 minutes.
That makes me
The
sad.
only thing.
That makes me really sad, Emily. This
Not
is
your fault. It's our brain. It happens whenever you're like many hours doing it. Even though you get it, your brain is just exhausted. So don't put it on you. It has nothing to do with you.
okay. All right, and then so that would be in the pulmonary artery because that's bringing deoxygenated blood. Well, not deoxygenated. It's like less oxygen. You know, that's what I was taught to say. Deoxygenated. Anyways, it's less oxygenated, not very well oxygenated, whatever the hell, however you said it. And as gas exchange occurs, obviously over to high to low gradient, then the partial pressure of oxygen will be higher, about 100 milligrams of mercury, and the PCO2 is about 40 milligrams of mercury. Now, as everybody sees right here, right, I just want everyone to see, there's only a difference of 6 millimeters of mercury. Only a difference of 6 of the PCO2. And that, my friends, is why the chemoreceptors are more sensitive to the amount of carbon dioxide, not to the amount of oxygen.
Didn't get that.
Okay. Because, okay, so when you're talking about the chemoreceptors, you're talking about, we're going to get to it next, it's coming up. You're talking about the receptors in which monitor the pH, and the amount of PC or the partial pressure of CO2 in the blood, including oxygen, sort of. Okay. But mostly those two things. And why it relies more on CO2, one of the reasons is because there's a little, you see how little that is? 6 to 40 or 46 to 40. That's so little. So if you can imagine that if this increases to a greater extent, there's going to be more, it's can change rapidly. You get what I'm saying? Like if it's so little, then if there's even a little bit more than normal,
They're gonna become sensitive.
yes, yes.
Okay.
Yes, they'll be sensitive to this in a normal person because this shouldn't change. It shouldn't normally change. But in someone who has emphysema, like Zadie was talking about, did I say your name right? Did I say it right?
Yes, you did.
Thank you. Yay, makes my day. Okay. Like she was saying, in emphysema, the people, they basically have constantly elevated levels of CO2.
So they just become like whatever, like it's normal.
Yeah.
Their chemoreceptors.
They're like, whatever, I don't really care anymore. You're really just like telling me over and over again. At this point, I'm just like tired.
They become insensitive.
Yeah. Yes. And so then, but in a normal person, they're sensitive. And how they can be so sensitive is because that's such a small amount right there. Just so small, right? So like she didn't really talk, she said it a little bit, but she stopped herself because she didn't want to get into it. But that's one way that you can kind of think about it, because in this, you see how big this is, 40 to 100. Imagine how the chemoreceptors would be stimulated every 5 minutes, or if it was like that sensitive, right? So we're gonna get to it in just a second.
I got it.
Yeah, you got it. All right. Now this is something we're gonna get to that in a minute. I want to get to another place. There was a question on one of the slides about this. So basically, if I have the alveoli that is just not working, it's not doing its job, and it's not because we're not supplying with blood, it's just not doing its job, and your body's like, yo, this is enough. What do you think it would do to the vessel that's supplying the alveoli? Would it constrict or would it die?
It would be constrict, because if it's not working, it's not gonna send it there.
Yes, it would constrict. And it would constrict because it doesn't want to, like you said, it doesn't want to send blood to a place where it's not being oxygenated or whatever the hell, however you say it. I can't say that. I need like phonics or something, because I cannot say deoxygenated, like, is that how you say it? Yeah. I don't know. Whatever. We're not going to talk about that. But I literally cannot say that. Did anyone ever notice that? Like, somebody got kicked off or something? Probably Jack Saint. Was it Jack Saint or did you?
Emily just sent us a text message.
You talking about deoxygenate?
That she was tired. She was gonna go.
Jack saying, I think you say it worse. Our accent. So Olivia, you're good. You're good compared to us.
Well, deoxygenate.
No, you said it right just there.
You haven't talked all day.
Night. Oh, I'm here. I fall asleep for like 30 minutes on y'all. I'm sorry. I wake up back, but I catch up pretty well.
So I hope something kicked in the sleep.
In the sleep.
A little bit. That's but I'm back.
Anyways, all right. So then matches ventilation to perfusion. So basically, if it's doing well, it's going to perfuse more. So if you have an alveoli that's doing its job very well, then there's going to be a dilation to that capillary and allow more blood there so that perfusion may happen.
Yes.
And what does it mean by perfusion? It's just taking that how it's supposed to go through the system, right? Whether it's a gas exchange, sending the carbon dioxide out and then just sending the oxygen to the organ.
No.
So well,
no. So this is just talking about how it's Yeah, perfusion of the gases across the gas exchange, but it's this specific thing is the mechanism is talking about it wants to local control mechanisms basically dilate vessels that perfusion is highest and constricts to areas that perfusion is lowest.
Lower, okay. So perfusion highest, it means it's perfectly working. The other one has a problem, so they don't even bother. The base vasoconstrict something, and then the other one dilates.
Yes.
Okay,
Yeah. Look at you.
I remember.
You get top that.
All I needed was bread. Sadie, don't judge.
For your brain.
Hey,
Your
that's
brain.
my
All right.
ATP.
ATP. It's glucose, carbohydrates. All right. Chemoreceptors. Sensitive to changes in pH, PCO2, and O2 lesser. Okay, time for graph, everyone. So we have two that we're going to be talking about. We have the peripheral chemoreceptors
And the central
and
medulla.
central chemoreceptors. The peripheral chemoreceptors are on the aortic arch.
And they respond to low oxygen.
They do. And the carotid bodies, and they're located in the carotid bodies, which are right here. The central chemoreceptors are located in
the
the
medulla.
medulla oblongata. All right, there we go. The medulla, which is right here, right there. Okay. Okay. So this is wonderful. Now we're gonna
Can
write.
you repeat that again?
Okay, the peripheral chemoreceptors are located on the aortic arch in the carotid bodies, which are right here. And the central chemoreceptors is located on the medulla oblongata, or the medulla, whatever you want to call it, either way.
They keep the peripheral chemo are located in the, I'm a slow writer.
The peripheral chemoreceptors are located on the aortic arch and the carotid bodies.
Aortic arch and carotid
bodies or sinus, whatever you want to call it.
Bodies. And the central?
The central in the medulla.
On the medulla oblongata?
Yes.
I keep saying ma'am because I haven't had sir, but yes, sir.
I say medulla oblongata, you guys say medulla.
Medulla oblongata.
That's all we have to know about those two?
Okay, now we're going to talk about this. You need to know this, what I'm saying next. And why I said the thing that I said before is because you should know where it's coming from, or you have no idea. Okay, so you have to know. All right. The peripheral chemoreceptors respond to
low
oxygen and low carbon dioxide, and it responds to H+ ions, which just means the acidity. It responds to the pH of your blood too.
Carbon dioxide is CO2, right?
Yes, PCO2, the partial pressure of carbon dioxide in the blood.
Oh, PCO2.
Yes, sir.
So you said the peripheral responds to low oxygen, low PCO2, or low CO2?
Low PCO2 and low PO2. Just think of everything that I'm saying is partial pressure. It's all the partial pressure of everything.
Okay. Low PO2.
Wait, no. I think the peripheral responds to high CO2, right?
Yeah, no, I was just saying what it responds to. I wasn't saying what it does. It responds to high levels of CO2.
And low levels of oxygen.
Yes.
Oh, I put it responds to low oxygen and low CO2.
No. High levels of carbon dioxide or PCO2 and low levels of PO2. And the PO2 needs to be lower than 60 milliliters of mercury. Anything lower. If it is not lower than that, it will not trigger this.
The PCO2
Yes. No, the PO2.
lower than 60.
Lower than 60 milligrams per mercury. And this is very important.
May God help me. All right.
All right.
So
That's
it
how-
responds to low oxygen, high PCO2, and high PO2.
Low PO2.
Low PO2, only high PCO2.
Yes.
All right.
Yes.
High PCO2 and low
And
PO2.
low pH.
P what?
Low pH.
pH.
Something else. Low pH.
Low pH.
Low pH level. Okay. Gotcha.
Okay. Now.
What about the 60%? I'm sorry. And you say it cannot be?
So for the PO2 has to be lower than 60 in order to trigger this. So just put PO2 lower than 60. If
It's here in this picture, guys.
it would not, yeah, it's gonna be in the picture.
Lower than 60.
And 60 to trigger.
To trigger what? Exactly.
The peripheral.
Okay, to trigger the peripheral. I spell everything wrong, but
That's fine. You'll understand it once you see it.
peripheral.
We just have
I
to
put that in parentheses.
put the answer.
All right. And then, all right, moving on.
All right. So now to understand why we're talking about pH, okay? When you have a high presence of PCO2 or carbon dioxide, your pH is going to lower and you're going to have something called acidosis, which is a pH below
7.4.
7.4.
Yes.
Okay, so higher
Alkalosis.
PCO2 causes lower pH.
Yes.
Okay.
And that is called acidosis.
Yes.
If you hyperventilate, if you are breathing in so much oxygen and you're not using it, your carbon dioxide is going to go down. And if that goes down, this can cause alkalosis. And that is a pH above 7.4. And your chemoreceptors don't really care. They don't care.
Wait, so is that why they use the brown paper bag to kind of get like
Yes.
the oxygen?
Yes.
Okay.
Because you will pass out. You will literally pass out because your body thinks that you have a high blood pressure and it will constrict the vessels to
In the
your
brain.
brain, and therefore it will literally just make you pass out because you're like, you just constrict the vessels and there's not enough blood, and that's why you pass out.
Is that caused by lower levels of PCO2?
Not P, CO2, carbon dioxide.
Yeah, low levels of PCO2, partial pressure of carbon dioxide.
Okay, so low levels of PCO2, right?
Yes.
So low levels of PCO2 causes
Alkalosis. It's right on the screen if you need to know the spelling.
alkalosis, okay.
Which is a blood pH above 7.4.
Causes pH increase 7.4. So it's gonna be more. Well, actually, isn't 7 going to be in the middle? No.
No. Okay.
Almost
When
neutral.
you're talking about water, yes. 7 is neutral. 7 is not basic, it's not acidic, it's neutral. When you're talking about normal blood pH, it is 7.4. It is not 7.
Okay.
And it can be, she said there's a range, and there is a range. I was taught the range was 7.35 to 7.45. So
So
but-
once we have the blood on 7.4, it means we could just, is that the when you could die, you said something like that? Or drop to the floor? Or
what?
how? What do you say? Something
Pass out.
No,
So
we're
yeah,
talking about hyperventilation.
I'm killing people. I'm sorry.
Hyperventilation.
Hyperventilation.
Okay. Now let's go on to the next part of the diagram / tree / whatever you drew. Now, the most common cause of acidosis, which is what we just talked about, which is elevated CO2 causes acidosis. This is called hypercapnia.
Acidosis?
Okay, when you remember when we talked about that elevated levels of CO2 means that there's more hydrogen plus ions in the blood, which means it's more acidic and below 7.4.
But not like acidosis in your stomach. It's gonna be in the blood. Because that one confuses me.
Oh, that's nice. Yeah,
Cause,
acidic. It's just your pH blood. It's gonna be more acidic.
so this is called hypercapnia. Hypercapnia is elevated CO2. That's what it is.
Okay, the one on top. I was just reading the hypocapnia, the one at the bottom.
Okay, that's hypocapnia. Yeah. So that is lower levels of CO2. Okay. So this is a lot to unpack. This is a very convoluted slide, but I think we all got it now, right?
Yes. Thanks to you.
Zadie's sitting there like, oh my gosh, again, the same thing again.
Can we just like move on to the next?
She's like, I gotta be up at like, I don't know how early tomorrow, and I'm tired already. How's your baby?
He's sleeping here next to me.
Oh,
My husband took him out of the crib and put him on the bed.
Isn't that beautiful?
I know.
she's like, I didn't want him sleeping in the bed. That was
No, not at all. Like I love him, but I'm not the type of person that likes co-sleeping, you know?
yeah.
But
I don't think it's good. I don't think.
yeah, but my husband likes it. So I'm like, whatever. I enjoy it now. Like I like sleeping with him now.
You like it now, but eventually when you're
Yeah.
gonna meet your time with him,
I
like,
like it, but I don't love it. Like, yeah.
you wanting to be in the bed and you're like, oh, get out.
Mm-hmm.
You're like, I want to sleep with my husband.
Mm-hmm.
Just minutes. Be back soon.
All right, so this is just showing you how it's stimulating things and how it's doing that. And it's, it is what it is. All right, so this is just saying that the chemosensitive area and how the H+ ions affected that. You don't need to see it. I don't care about that. Really, she didn't talk about this either, to be honest. No. We talked about this. Peripheral chemoreceptors are stimulated by the rise of blood H+, which means pH. Lower pHs, it stimulates this, and that's because of hypercapnia, which is the elevated CO2 levels. And she said that she's not going to ask. Those are two together. These two are like pH, lower pH and higher CO2 levels. She's not gonna make you differentiate between it. They both do the same thing. That's what she said. They both do the same thing. Don't freak out. And
But
they
she
both.
does want us.
Sorry, go.
Wait, what?
Go, Zadie.
She does want us to know that peripheral chemoreceptors are the only ones that respond to low oxygen.
Yes. Yes.
Indistinct from the central chemoreceptors. They don't respond to low oxygen.
Yes. And they respond quickly and they increase ventilation. It means they increase breathing. Nope. Okay, hyperventilation, like I said before, decreases CO2, brain vessels will constrict, cerebral ischemia causes you to pass out. Ischemia, it means low blood. Really? Is that what that means? Yeah.
Ischemia.
Ischemia.
What does it mean?
Ischemia, well, my grandpa has that. So it's like when no oxygen, it's getting to your brain for like a couple of seconds. So it's called transient ischemia. So it's like you're there, but your oxygen doesn't get there. So you're just like dead for a couple of seconds and then you need to resuscitate like often.
What?
Like brain dead?
I don't know. It happens to him very often. But my mom, she's the doctor, so she knows how to resuscitate. But it happens very often. And
Really?
also, you could
So
see that by
scary.
the color of his skin. He turns this yellow color, and it's not jaundice. It's just like yellow, all yellow. And yeah, it happens very often. So now we're just getting used to it. The only day I'll be like really upset is once he actually doesn't resuscitate. But he's 91, so he's like, please
Wow.
leave me alone, and we keep on just resuscitate every time it happens.
Wow.
Plus, he doesn't eat bread like me. He has like this specific diet. It's very, very healthy and good. So he's probably gonna be living longer than me.
He lives here or in Cuba?
With me, I brought him here home.
Oh,
Yeah,
so
so I have my
nice.
mom take care of him only here in the house, and then I'm just the one doing everything.
That's good.
Mhm.
All right. So
So as ischemia. Sorry.
yeah, thank you.
I'm sorry.
Yeah, it's okay. I like hearing people's stories and all that stuff. I think it's cool.
We learn.
We learn, that's for sure. All right. Will you breathe in a paper bag to increase the CO2 levels? Effects of blood PO2, direct stimulation only at the very low arterial PO2 levels. Okay, so this is what I said before. Below 60 milliliters of mercury. Okay, so the normal is 100. So a 60 is really low. When that kicks in, this causes hypoxic drive, which just means that you're just starting breathing really heavy. You're trying to get as much oxygen in you as possible. And it's a direct effect of the PO2 on the carotid arteries or the peripheral. And the effect is dominant over all others. Even if you're affected by the CO2, if this kicks on, you're really just going. You're just like, I don't know, you're just like going really hard. I guess, I don't know. However you are, it's dominant.
Less
Yeah.
than 60 is hypoxia, right?
What?
Less than 60 would be hypoxia.
Yeah. All right, so this is just showing you there's one exception. Individuals chronically elevated CO2 levels, like we talked about before. There's also a genetic variation, like people with COPD, asthma, emphysema, etc., often refractory to the chemoreceptor regulation via the CO2, which just means that they respond only, they stop listening to the elevated PCO2 levels. So they don't get stimulated by that. The only thing that their peripheral chemoreceptors do is if the oxygen levels are below 60, then they'll kick on. And most of the time they'll come to the ER and you'll give them oxygen, but you can't give them too much because then they'll lose their drive to breathe, and then the blood gas volumes will worsen. So you have to give them a little at a time.
That's people with what?
Emphysema, COPD, asthma, really pretty much probably emphysema.
That you cannot give them a lot of oxygen.
No, you can't. You have to give them like very little. You want them to use it as little as possible because what happens is they just will stop. I'm guessing that there's probably more to it and we'll learn about it, but she said that you don't give them a lot because if
Okay.
you, then they'll stop breathing.
Okay.
All right, so we're towards the end, guys. Okay,
Yes.
this is just showing you, you know, the PCO2 levels in people who are, you know, normal, and as PCO2 was, I don't know, it's just bad. I can't explain this graph. I'm sorry. I have no idea. I tried like yesterday and I was like, no, just can't do it. So it just is, it is what it is. Oh, I think it's showing you that the amount, so if you have higher PCO2 levels, your body will start respirating more. And like in this case, metabolic acidosis, which means there's more H plus ions. And if there's more H plus ions, then there's elevated CO2 levels. And so the basically the drive to respirate will kick on. So the higher the PCO2 levels, the more ventilation you'll have. And that's normal, right? So even right here, so the higher, so if you're awake, the more you, well, I don't know how this one, but this one, so then this one, you see how it just doesn't respond as well?
Yeah.
The chemoreceptors just don't respond to high levels of CO2, especially those in deep apnea. And oh god, can't say it. When you're too tired, you can't even say words anymore. Deep anesthesia.
Anesthesia.
Okay.
I
So
can.
this is hypoxic drive. Chronic. What?
Can we really go over that one?
This one?
Yeah. You don't want to?
All right. So oxygen, oxyhemoglobin. Wow, that's a beautiful line. Oxyhemoglobin is basically oxygen with, or hemoglobin with oxygen on it. Even if one site is occupied, deoxyhemoglobin is deoxygenated hemoglobin. Methemoglobin is when the iron becomes oxidized, which means it's a +3 or phrenic form, and it cannot bind oxygen. And because that you need +2 to bind oxygen, not +3, and there's just a small amount normally. And carboxyhemoglobin is when heme combines with CO or carbon monoxide, not oxygen. And this binds to a much higher or stronger affinity. And the treatment is a hyperbaric oxygen chamber. Any questions?
So from this slide, what do you think we need to know? Like the difference between the oxyhemoglobin, deoxyhemoglobin?
You should know that. It's pretty easy. And the hemoglobin, that's pretty easy to know that. I mean, pretty much, I mean, don't know all the entire slide, just know the key points you talked about, which is the stuff that I talked about. The methemoglobin is it's the one, the cells that cannot bind oxygen because they have a +3 form, which they need a +2 form, and there's you know, a couple hanging out in your body, and that's why you have less than 100%.
And that was the oxygen binding. So the oxygen isn't able to bind to the hemoglobin if it has a +3. It has to be a +2. Is that what you're saying?
100%. Yes.
Okay.
And how do you say that? Methemoglobin?
Methemoglobin.
Methemoglobin. That's the reason why, like Olivia said, 97% of the blood is saturated, like not 100%.
And can we just briefly explain why it wasn't fully saturated again and why it's at 97%?
Because oxygen doesn't bind to all of them,
got it.
to all the
Got it.
hemoglobins.
Okay, makes sense. And sorry, can you repeat what deoxyhemoglobin was? Because it doesn't say it there. I didn't get to this part of the lecture yet, so I didn't even hear.
Hemoglobin that doesn't have oxygen on it.
Okay, duh. Like, wow, that was so simple. Okay, thank you.
And carbon dioxide hemoglobin is when heme will combine with carbon monoxide, like carbon monoxide poisoning, right? That. And it's not oxygen, obviously, and there's a much stronger bond and a much greater affinity for it. So it will basically kill you and very easily.
Hey, you
And
say kill someone. Don't say now it's drop. I heard it.
and the only thing that can really help you is a hyperbaric oxygen chamber, because this will knock off some of the bonds and it can help you if you're caught in time.
Is heme the same thing as hemoglobin, just said in a different way?
What? Wait, him?
Oh.
No. Okay, him, I'm gonna give you probably not an easy explanation. So when we have red blood cells, they get destroyed. They have, every cell has this iron in the middle. I think it's iron. That iron is recycled to every newer cell. So these ones is destroyed or removed. They heme is in the middle. That's what helps you bind oxygen. So you need that heme, which is that iron, and that one is recycled. Even though you just clean the old cells and like put it away, you keep on reusing that heme. So heme is just the iron in the middle of the hemoglobin that allows you to bind to oxygen. Without that, you can bind to oxygen. And hemoglobin is just like the actual red blood cell.
Right. Okay, so heme is the iron in the middle of the hemoglobin, and it helps bind oxygen.
Yeah.
Okay, thank you. I remember that, but very vaguely.
For some reason, it stayed there.
Okay, cool. Got it.
I think we're there. I think we're at the end, guys. I think, oh, well, this, okay. Percent hemoglobin saturation. So it's it basically puts a light, and hemoglobin, when it has oxygen on it, shows a certain color. And so that if you have, it's an indication of oxygenation, whatever the hell you say. And normal arterial blood was about 97%. It's not 100% because the methemoglobin, each form has a slightly different color. It absorbs light differently. And the measurement simplified, it's a pulse oximeter, pulse AO2. What? I don't know what that means. She didn't talk about it. I'm not going to think about it. Yeah, so that's it. There we go. Oh. Oh.
Oh.
Oh my God. She went over all this?
I told you guys this PowerPoint was
Over
hard.
this. No, she didn't go over this.
We didn't talk about curve shifts.
No.
We stopped actually.
No, we didn't talk about curve shifts.
When we did.
Up here.
Where? What slide?
The one before curve shifts.
At rest, large amount of O2. Nope. Nope. Nope.
The sigmoid one.
Nope.
We spoke about that.
Sigmoid shape. Where it says sigmoid. That one. That one. That's the one that we stopped.
Okay.
But she probably skipped a lot of pictures and stuff.
Okay.
That
So
one we're done.
let me just take it like a second. Brain work. All right. Okay, hemoglobin concentration determines oxygen carrying capacity. Low hemoglobin. As you can imagine, blood O2 content will be low if there's low hemoglobin, because it cannot transport oxygen. High hemoglobin, there's going to be a high oxygen content. Compensatory increase in response to altitude, smoking, and rigorous exercise. We talked about this, how if you have hypoxia, it stimulates your kidneys to produce erythropoietin, and that will stimulate red blood cell production in your long bones. Androgens can also stimulate this. She did not talk about it. But males do have a higher hematocrit and hemoglobin because, well, they're bigger and they have more testosterone, which is an androgen. Oh my gosh, Sadie, me. That's me. You're like, you're so tired. You're just like, I want to die.
I am. And we have class tomorrow.
I have to present.
Me too. Ew.
Present today. I wasn't ready, and like some of our team members weren't there, so I had to present for them.
No, I
I
got
no clue what to say because
Guys, in my group,
like
there was. Pause it.
Don't say anything. I hope. All right, so oxygen unloading and loading oxygen combines with deoxyhemoglobin, occurs in lungs. Unloading reaction. Okay, this is just saying the gas exchange occurs and the oxygen comes on. This is showing you that before any oxygen is loaded onto the thing, that these little things are like kind of smaller, so it's harder to load the first one, and then every other one is easy because it opens.
Yep.
Okay. And as you can see, this one comes on and then they all can just easily get on there. But the first one's a little bit difficult, but everyone else, it's perfect. Okay. Direction of reaction, high POT favors loading because loading onto the hemoglobin because it wants to carry it to places where it's not high. Okay, high POT, partial, so low partial pressure, like in the tissues, it favors unloading. So the hemoglobin will release its oxygen so that the tissues can get oxygen, obviously. And affinity of oxygen for hemoglobin, if it's too strong, then it will hold on to it when it needs to release it. And if it's too weak, then it will release it when it doesn't, when the tissues don't need it. So it's near perfection in this matter. So this shows you that as the partial pressure goes down, so does the amount of hemoglobin or oxyhemoglobin. So as you can see, and this was before, you see 40 and 70. So that was the resting cell was 40, PO2 of 40, and the 75 was the loaded, was the amount of loaded oxygen, well, amount of hemoglobin that was loaded with oxygen. This is the same graph. Okay, last slide, everyone. Dissociation curve, systemic arteries. The PO2 is about 100 millimeters of mercury, and the hemoglobin is very saturated. In systemic veins, the PO2 is about 40 milligrams per mercury, and the hemoglobin is 75% saturated at rest. This would be less saturated at if you're exercising. Blood entering the tissues, it will be about 20 milliliters per 100 milliliters of blood. That's oxygenated. And blood leaving tissues, it would be about 15.5 per 100. So 22% of the oxygen is unloaded in normal rest at the tissues. And further increased demand would reduce the partial pressure of oxygen in the blood, and because more needs, by the tissues. And that's it. That's it.
You made it.
Wow.
Wow.
My brain
I
hurts.
don't even want to know. Okay, I don't even want to know how long that recording was.
Probably really long. Oh wait, you're still recording.
Try to stop at like 4